হ্যালো চন্দন স্যার।
Hello.
এই তো হয়ে গেছে।
Hello. Good
হ্যাঁ,
afternoon to all of
বলেন।
you. Sajal, can you hear me?
Yes, sir, you are audible.
Okay,
You are
fine.
audible. So, welcome all the participants for this today's post-lunch session. So, in this session, you have two lectures. One will be given by Professor Pranab Ghosh. He is a senior teacher of our department and also the register officiating of North Bengal University. And the second lecture will be delivered by Professor Ashish Pal. And I just request the participant just to introduce Professor Ghosh for this session.
Good afternoon, sir. I am Dr. Chandan Bhomik, Department of Mathematics from Sohid Nur Islam Mahavidyalaya. Welcome you all in this refreshers course online platform. Today now introduce eminent speaker Professor Dr. Pranab Ghosh. He is a professor in organic chemistry, University of North Bengal. He is a fellow member of International Congress of Chemistry, Indore, Madhya Pradesh. He is a live member of Chemical Research Society of India and also member of Indian Chemical Society. His research area is natural product chemistry, polymer chemistry, and organic synthetic and synthetic methodology. He is supervised 26 PhD scholar and have 8 ongoing research scholar. He has 25-year experience in research and teaching and 7-year experience in industry. He has published more than 182 research articles. With this brief introduction, I now request Professor Ghosh to deliver his lecture. Please welcome, sir.
Thank you, Professor Chandan Bhomik and Professor Sajal Das. The Sajal Das is the coordinator of that refreshers course, and uh, and also good afternoon to all the teacher participants, my colleagues, would be my colleagues. So in this refreshers course, basically, as because it is a refreshers course, so chemistry and related matter, not chemistry, I would say, the theme of the refreshers course is some sort of relationship is there with material science. So I think you have uh, receiving much lectures on the topic of material science. So as because I have other areas of research also, but looking into the theme of the refreshers course, I'll confine to one of my favorite research topic, which is the additives, its research, its preparation, its evaluation, as well as its application in the field of lubricating oil. So as you know that, yes, lubricating oil is a bit of inert things, the hydrocarbon, mostly the hydrocarbons. In some cases, some silent functional groups are also there. So our earth is a huge source of lubricating oil. I should not say huge because day by day it is becoming less and less. But although this is consumption is much high, but still we have enough. Right now, we do not have to worry about the natural abundance of that lubricating oil. It was there, it is there, and it would be there. Now, the lubricating oil as such is used for the lubrication of machineries. In some other applications, it is also being used. Now, if we consider, yes, the fuel economy, if we consider the rate of consumptions of the lubricating oil, then we have to tackle it, we have to handle it rather, not to tackle, we have to handle it with some additives which can add, which can add additional performance to that lubricating oil. So it will have the role to make it compatible to the engine technology. Number two, it should reduce the consumption and at the same time it would provide the fuel economy because we are nowadays in the crisis of consumption, and we are in the crisis of fuel savings, this thing that is, in short, it is called fuel economy. So lubricating oils are there, plenty are there, but at the same time we used to reduce its volume of consumption, and at the same time the most important thing is you have to add the performance into it. You have to add, I repeat, you have to add the performance into it. Now you see, in earlier century, right, there was lubricating oil as such, and people used to use it. People used to use it as such without adding any treatment, without adding any additives, without adding any chemicals into it. So it was as such obtained from the nature. People used to get it and run their machineries, including the vehicles, 2, 4, and the heavy vehicles. Now, that time, although it was used as such, but the thing was, it it was devoid of so many performances, which nowadays people have felt it is really necessary. Number one is the consumption of oil. If you run your vehicle without using any additive, without using any performance into it, then the mileage people used to get in the 19th century, earlier of the 19th century, say 20 liters and 1 mile. So mileage is, you can easily consider. That was the equation. Per mile, we have to use 20 liters of oil. That was the mileage. And as a consequence, there was damages of the lifetime of the vehicles and any kind of machineries. So people used to throw it 2 or 3 years after. You have to buy a new vehicles, right? And the capacity was also
Excuse me,
not
sir.
up to the mark.
Excuse me,
Yes.
sir. Sorry to interrupt, but are you presenting? Are you presenting? There is no PPT actually.
I'll show
Are
you.
you
Don't worry. Don't worry. I'm just giving you the introduction.
presenting?
I'm
Okay,
just
okay.
giving you
Thank
the
you.
introduction. Okay.
Okay.
So this was the earlier decades. People used to use it, right? So mileage was very, very less. Longevity of the machine was very, very less. So as a consequence, people started thinking about it, right? If we use per mile 20 liters of the oil, then in future, very near future, we will be losing the lubricating oil obtained from the natural resources, right? So this was the original, and at the same time, each 2, 3 years after, you have to buy a new vehicles, right? Then people think about something has to do. Mostly the original equipment manufacturers, the OEM, and consequently the people, those who are involved in chemical treatments of so many things. We have to do something for that. And at the same time, if you use high volume of oil, then the thing is pollution. Pollution has to be controlled, because if lubricating oil burn in the engine, we'll get carbon monoxide, we'll get sulfur material, NOx, SOx, etc., etc. So that was another problem during time, and it is rightly, it is very alarming to us. Okay, so considering these drawbacks of using the lubricating oil without using any performances into it, people started working in it. And in the decades of 1990 onwards, yes, most of the equipment manufacturers were tried to add the performance into it. Okay, so that is the basic concept. We started our research in this direction to solve the present issues. Okay, I had the experiences in working with the uh, number one, that lubricating oil industries in India, that is Lubrizol India Limited, which has collaboration with Lubrizol Corporation USA. Only one company is there, that is multinational with government of India. The share is 59, 61, 41%. So that Lubrizol India, they develop They manufacture, they do R&D, and they market it via IOC, BPCL, and other terminals. Those who are having the 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 that performance additive, those is actually sold through the terminals of IOC, BPCL. That's all. Okay. So now I will present today with you. Rather, I will share my experiences in this area of research with my PowerPoint presentation. Okay. Right.
Sir, you are muted. Please unmute your microphone. Sir, you are muted. We do not any sound. We do not have any sound.
We cannot hear you. You are muted. Dr. Ghosh.
Was it reached to you, my presentation?
No,
Yes,
sir.
sir.
No, could you able to see?
No,
Could you
sir.
able to see?
No, sir.
Could you able to see and hear me also?
Yes, sir, we can hear you, but presentation is not visible.
Is it now visible to you?
No, sir.
No, sir.
Okay, okay,
No, sir.
just a minute. I'm coming. I'm coming. Is it okay?
Yes, sir.
Yes, sir.
Is it okay? Is it okay?
Yes, sir. Yes.
Okay. You can hear me also?
Yes,
Yes,
sir.
sir.
Fine, fine. So this is the title which I have chosen is multifunctional greener materials as performance additives for lube oil. Okay. Yes. Lubricating has oil has got several names. One is lube oil in short. Another one is the base stock. Right? Yes. This is our future. As a teacher or students is our future. So we are I should acknowledge them first because they are there and because of that our future is there and they are our inspiration. I must acknowledge them also. Dr. Vipul Bihari Shah, yes, he has selected the member of IUPAC, the second Indian who is given who has given that particular prestigious position in the IUPAC after Professor C.N.R. Rao. He is Dr. Vipul Bihari Shah, our alumni in the year 1976. He passed MSc from our university. Second one is Dr. Partho Sarathy Chakraborty, our Bhatnagar awardee in the year 2018. He is also our students. He did MSc from our university and BSc also. Professor H. Pal, he is now in scientist H position of Bhabha Atomic Research Center and is heading the molecular photochemistry section in BSc Mumbai. And Himanshu, the professor Himanshu Shekhar Bose, he is doing nice over there in the Mercer University School of Medicines. He is also our alumni, done MSc, PhD, and BSc also from our university. Dr. Shanta Dhar, yes, she is also our proud. She is now doing biology and chemistry mixing up in the University of Miami, Miller School of Medicines. And some more to mention is Boishaki Majumdar. She is in an industry, in a packaging industry. She is also heading that particular department. And Dr. Santosh Kumar Ghosh, yes, our alumni only. She is also a faculty of Case Western Reserve University. So, Professor uh, Satyabrata Samanto is also there. Yes, he is senior polymer scientist and project team leader. He is also doing very good in USA. So they are really inspiration of us as well as our students, right? So we are really proud of them. Now come to the lecture.
Excuse me,
Sir,
I'm not
sir,
able
your
to hear
presentation
you.
is not visible. Yes.
Pardon?
Probably you just stop sharing button. Press the
Is
stop
it?
sharing button.
Let's see. হ্যাঁ স্বপন স্বপন বলো হুম 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 ঠিক আর সিলেকশন কমিটিতে কে আছে আচ্ছা ডিনটির নাম নেই ডিনটির নাম নেই দেখো আবার জানি না দেখো তুমি তুমি যে সামাল দিও জানো ঠিক আছে ফাইন না উপরওয়ালা কথা বলে নিয়েছো তো ফাইন 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 ঠিক ওকে ওকে হুম হুম ঠিক আছে যখন পরে কথা বলি HRDC ক্লাস নিচ্ছি 4টের পরে হ্যাঁ ঠিক 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 Is it visible to you now?
No, sir.
No, sir.
No, sir.
Till now, no worry. Share. Gone. Is it okay?
Okay, sir.
Yeah.
Is it-
Yes, sir. Okay.
No, fine. So this was I have already shown you, but you did not see.
Hmm.
Okay. So I must acknowledge our students because they are our future. I must acknowledge our inspiration, our dadas. Okay. So Dr. Bipul Bihari Shah, Parthasarathi Chakraborty, yes, a member of IUPAC, Dr. Bipul Bihari Shah, Parthasarathi Chakraborty, our alumni, passed from here. He is the Bhatnagar awardee in the year 2018, followed by some other award he has also obtained in his name. Professor H. Pal, he is heading the Department of Molecular Photochemistry of BSc Mumbai, our alumni. Professor Himanshu Shekhar Bose, yes, she is the faculty of Marshall University School of Medicine, Dr. Shanta Dhaur, Faculty Department of Biochemistry and Molecular Biology, University of Miami, Dr. Boishaki Majumdar, she is also doing very good over there. Boishaki Majumdar, yes, she is also heading that packaging development technology. She is the head of that unit. Yes, and Santosh, yes, she is also there, faculty of Case Western Reserve University, and Dr. Satyabhusha Samanto is also there. He is also senior polymer scientist and project team leader, doing good in USA. They are some of our alumni doing good in abroad, and is inspiring our students always. Now come to the title lecture. Multifunctional additives, and they are adding performances in the lubricating oil. So the things will be discussed with you is general introduction. A bit I have already done in the introduction session without the PowerPoint presentation. Then the background, little bit of background that I will give you, and a brief of recent contribution of our group towards the development of lube oil additive LOA, and obviously some bibliography, right? So this is the container where performances is added. The container is containing the lubricating oil. So that way I am making the presentation to you, right? Now the thing is, the title things, lubricating oil or lube oil. As I mentioned, it is also known as the base oil because this is the basic fluid with which we can play around to give the performance to any kind of machineries, right? So they are the primary building block of a lubricant. Lubricant is the lubricating oil plus the additives, the chemical additives, right? They are the as a whole called lubricant. They are chemically they are the paraffinic, naphthenic, and in some cases aromatic hydrocarbons with a wide range of molecular weight and varying viscosity, density, etc. So lubricating oil is a complex mixture made of mainly paraffinic, naphthenic, and aromatic hydrocarbons, and their physical property also they vary in molecular weight, viscosity, and density. So this is the lubricating oil. Now, what is the need of it? You can easily get from this comedian picture, right? Say in dry, when lubrication is not there, see what happened to the fellow, and when it is lubricated to that green line, lubricated, right? You can see how happy the person is. Rather, he cannot keep pace with that lubrication, right? So this is the beauty of a lubricant, right? So when lubricating oil is getting some performance into it, convert it into lubricant, and this is their function. So from there you can get what lubricating oil and a lubricant is doing for the machineries. Now the importance of lubrication technology. Oh, this will not be visualized by you. Anyway, now the basic thing, the production from a barrel of crude oil. You know that the lubricating oil, you can say the diesel, petrol, etc., etc. The major source is the crude oil, which is obtained either under the beneath of our earth or at the upper surface of that. The Oil India Limited, they are taking the crude oil from the upper cut, from the surface of the soil, and the Bombay High one, that is the ONGC, Oil and Natural Gas Corporation, they are doing it under the sea, and from there they are taking them out. So crude oils. So that crude oils contains a lubricant, but their percentage is only 1%. That is really a great disadvantage to us. Although we are getting so many things out of that, but the one which is important for running the machineries, its percentage is very less, only 1%. So you have to think for that. You have to make a conservation of that. You have to make the machineries to make them fuel efficient, and we should take care of the engine also to make them so that they cannot burn much more of the lubricating oil as such in the air. So we can see that the lubrication world is a very small part of the overall refining business. নানান ক্লাস নিচ্ছি পরে কেমন? Now the uses of lubricant. There are industrial uses and one uses is there in automotive industries. Right? So if you consider that, then you can see automotive lubricants are about 50% of the total lubricant market. And engines are over 80% of that. Consumption in the automobile industries is 80% of that 50%. This is the driving force for most of the lubricant research. Yes. So market is huge, demand is huge, but the natural abundance is a bit less. So do some research on it so that we can conserve it. If we can add some performance into it, then their consumption will be reduced, will be made reduced because of the added performance into it. Yes. So necessarily, it will take care of the following issues. Number one, as I mentioned, conservation of natural resources, the fuel efficiency, and protection of our mother environment. Right. So all the three are guiding us. Do something which can add performance into the lubricating oil, and that way reduces consumption. What is the prospect? Why people will do research in India and abroad also with that lubricating oils additive? The lubricants additive market is expected to grow a compound annual growth of 2.69% by volume over the next 5 years. And Asia Pacific, especially China and India, is the global manufacturing hub of the world, and as a consequence, is the largest market for lubricant additives. As a consequence, also Asia Pacific will continue to lead the market till 2027, right? So, who is doing the business in India? Lubrizol. Yes, they are doing both in USA and in India. BASF, they have their unit in India and Germany also. Afton Chemicals, basically the US based, Tiana Chemicals Group of China, among the various others. And this is collected from the Custom Market Research Services. So this is the data, right? So that's why, yes, it is alarming. So we can go ahead with the additive research in India because Asia Pacific, including India, is the largest market for lubricant additives. So considering the impact on it in the environment, we must add the greener also into it. So multifunctional. One compound can do so many, rather add so many advantages into the lubricating oil and considering its greener aspect. Okay, that is the thing which will be discussed, and people, many of the industries who are involved in it, and they are doing nowadays multifunctional and also the greener materials preparing, manufacturing. They are doing research and development into it and also market it. Now, how smart they are? These materials are how smart. I'm talking about the performance additives. Lubricating oil is the base one. We'll play with that, with our performance additives, which will be manufactured, which will be prepared in the research laboratory. Yes, how smart they are. They reduce the friction. Right. Friction has to be reduced, otherwise consumption will be more. They protect the engine machineries against corrosion. Yes. They add the cooling things into the machinery because when the engine in operation, its temperature goes beyond 400 degrees centigrade, which is not good for the any kind of machineries. Okay, so cooling is also very essential. And after running 1 or 2 years, then many particles generated into the crankcages. So we need to evacuate the particles. Who will do that? No, not the sweeper. We have to do it with our additives only. And at the same time, it performs in wide temperature range. If your temperature goes below in the hillside, it can go below the normal, as well as it can go up even at 43, 44 degrees centigrade. So equally, it will be effective in both low temperature as well as high temperature. That's why they are considered as very smart material. They reduce friction, they protect against corrosion, they are doing the cooling effect in situ into the machineries. They evacuate the particles also, which are in this thing diffused state within the oil, and also make the lubricating oil applicable both in the lower temperature as well as is the high temperature. Okay, just a minute. হ্যাঁ দিয়ে দাও
না সেটা না
হুম বেশি করেছে
তুমি তো অ্যাকশন দিচ্ছ
হ্যাঁ আমি অ্যাকশন নিয়ে আমি তোকে দিয়ে দেবো কি করে দিবি
এরা তো বন্ড সাবমিট করবে তারপরে তো
হুম
হ্যাঁ
আমি তোর কাছে পাঠাচ্ছি তুই ওটাকে ট্যাকেল করবি যা করার ওরা করবে তুমি ওদেরকে ইনস্ট্রাক্ট করবে
হ্যাঁ কাল তুই এটা তুমি দিয়ে দাও
হ্যাঁ
ডিজাইন বাড়ি ইউনিভার্সিটি করে দিতে হবে বন্ড এক্সিকিউট করে তারপরে অ্যাপ্লিকেশন
ঠিক
ঠিক আছে
ওকে yes now the composition of lubricants, can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Now the composition of a lubricant. As I mentioned, base oil or lubricating oil will be there, plus additives. Okay, so 1 drum is of base oil, another one is the additives manufactured in the chemical laboratory, and when we mix them together, they are called lubricant. Indian Oil Corporation has a blending unit, simply a blending unit there in Kharghar in New Bombay, okay, which is called IOBL, not IOCL, IOBL, Indian Oil Blending Limited. Thousands of employees are working there just for making them the lubricant. They are getting the base oil from the ONGC, right? They're getting the additives from mostly from the Lubrizol India Limited and mixing them together and making the lubricant. Then they are passing it to their terminals. BPCL is not having that blending unit. They are taking it from IOBL only, right? Now the background. Additives are in frequent use to improve the performance of the lubricating oil. Development of technology demands new chemistry to meet the specification as laid down by the manufacturer. Let me explain a bit. Now you can see various vehicles now flying in the cities, even in the villages, in the towns. There you will see the label BS stage 4, BS stage 3, like that. That is the specification I am talking about. This is the specification given by Government of India in consultation with the OEM, original equipment manufacturers. What is the background? The background is Tata will say to the Ministry of Oil and Natural Gas Corporation, Ministry of Oil and Natural Gas, right? They will say, we are developing one engine. It will only run by that kind of lubricant. So we need a specification to be guided from the government, because if they do not follow that specification, then the engine will die in 1 or 2 months. So that specification, government will give the specification in consultation with the OEM to that particular grade of vehicle, BS4, that will run by a specific kind of fuel, right? So once the terminal will see it is a BS stage 4, part of stage 4 vehicles, then they will put that particular specification wala oil into the crankages. Otherwise, it will not run. Even if it runs, then its lifetime will be reduced to a month or so, right? So that is the specification. So once they plan to make a higher kind of engine technology in a vehicle. You see, every year we see that yes, Tata is coming up with a new vehicles, Maruti is coming up with a new vehicles, etc., etc. So before that, before that they have a discussion with the research and development center of various industries, various institutions. Here's our institution. We are going to launch this kind of vehicles, and for that we need that kind of lubricant. Means lubricating oil be there, and the performance should be like that. So can you able to make it? Then only we will proceed. Otherwise, not. We will stop that technology. Then, after a thorough research and development into the laboratory, they will say yes or no. If no, then that particular technology will not come in the market. If they say yes, then only they will proceed for that new technology of any kind of machinery, maybe a vehicle or some other engines, right? So this is the background of making a specification and making a performance additive through the chemistry laboratory, right? So that's why the additives are in frequent use to improve the performance of the lubricating oil. So additive research is never ending process, because day by day new engines will come up. Therefore the R&D will be involved throughout the year in developing a particular lubricant for that particular machines, right? Therefore the objective is multifunctional additive. So many performances are being added. একটা পারফরমেন্সের জন্য যদি আমি একটা করে অ্যাডিটিভ দেই, তাহলে তো আমার 10টা অ্যাডিটিভ লেগে যাবে। Cost will be high. People will not be ready to buy it. Has to be cost effective also. Therefore people are looking for একটাই অ্যাডিটিভ তুমি তৈরি করো and add performance into it. That's why it is called multifunctional additive. And they should have low manufacturing cost. Yes, manufacturing cost has to be reduced. Otherwise, the selling cost will be in the higher side, will be bad for the terminals, will be bad for the common people, right? And your additive should take care of the environment. So these are the three main objectives of the additive research. It should be multifunctional. একটাই chemicals আমি তৈরি করব যার মধ্যে that functionalities are there. Too many functionalities are there. And its cost should be within the limit of the common people, and it should take care of the norms of eco-friendly environment, right? Now what is multifunctional additives? Now let us tell me the story. What is that? Say your vehicle is running with a particular oil found to be very good in the normal temperature, but when the temperature is getting reduced, then it is giving problem. In Siliguri in winter, the temperature will be around 30 to 33 degrees centigrade. But at the same day, if you go up in Darjeeling, the temperature will be around 10 or something like that. If the oil is sensitive towards the temperature, what will happen? In 30 degree, it will run nicely in Siliguri. But at low temperature, it is oil. So it has an effect on its viscosity, etc., etc. And even at 10 degrees centigrade, it may freeze also. If this is the case, then you will not be able to run your vehicle in Darjeeling, right? Which is flying nicely in the road of Bagdogra, Naxalbari, etc., etc. That was the problem initially, and this is the real story. At low temperature, where the temperature goes below normal, below 0 degree, then yes, vehicle used to stuck over there day after day. So we need to have some performances to be added into the lubricating oil. So if you first consider the freezing nature, our chemical should be in such a way assist the lubricating oil so that 33 degree as well as 0 degree should not affect its flow ability. It should flow even at 0 degrees centigrade. It should flow nicely also at 32 degrees centigrade. Is it possible to do that? Yes, people found that it is possible. If we go into the chemistry of lubricating oil, the thing is, as I mentioned, the composition of lubricating oil is paraffinic, naphthenic, and aromatic hydrocarbons. You know that paraffinic, naphthenic, it has, yes, wax crystal into it. Right. What is the nature of wax crystal? Yes, it has the waxy nature, and at low temperature, it will freeze. And this is there. The chemical composition of the lubricating oil is with them only. So naturally, if you reduce the temperature, what will happen? It will freeze. It will freeze. Yes. So what chemistry should do over there? Should I heat it? No, this is not a acceptable alternative. So we should fight it against another chemicals. Something is there which can prevent the wax to form a fine crystal network. If we can resist that, then wax crystal will not be in growth over there, and the flowability will be maintained even at low temperature. So you have to fight with them. So we have to input some material into it which can get into the crystal network of the wax. Okay, so one crystal will not be able to form the network with the other crystal below, because it will sit in between the two layers of the wax crystal. And if it is so, then they will not get the scope for forming the wax crystal network. As a consequence, flowability will be maintained as it was in Siliguri. Right. So that way we have to fight it. And for that, what is the needed? The first thing needed is your chemicals, your performance additive. Why performance? Because it is adding performance to your oil. What way? It is it is maintaining its flowability at low temperature as well as at high temperature. Right. That's why it is called a performance additive. Now, to reach to that goal, what is the basic requirement? The basic, very basic requirement is it should be oil soluble. If it is not in the lubricating oil soluble, of no use. No use. Right. The first thing it has to pass is its oil soluble. Right. Now, what is the composition of the lubricating oil? Yes. 40 or more than 40 number of carbons are there in a chain. Right. So, to make your additive compatible with that lubricating oil, it should be also a big chain. That's why mostly people are using the polymer, because polymer contains a long chain, right? So polymers can be added to that. What kind of functional polymer? Which can take care of the event, as I mentioned, which can get into the network and get them separated. It has to be nicely soluble in that particular lubricating oil, and it will make the crystal network, the crystal of waxes separated. Okay, so a particular kind of chemistry is working over there. Right, acrylate chemistry, polyacrylate is using nicely over there. Polyacrylate, polymethacrylate. Even nowadays, some of the biodegradable oil is also working nicely over there. So if I can get the biodegradable oil, if I can get the biodegradable polymer using for the same purpose, then it will meet the additive performance. Yes, making your oil using nicely in the high temperature as well as low temperature, one criteria, and has to be cost effective. And at the same time, if it is a biodegradable, if it is a naturally occurring oil, then it will also take care of the environmental issues. Okay, so that can be. So what I mentioned is taking care of the flowability of the oil, which is called pour point depressant, which is called PPD in short. Pour point, pouring. This is the figure you can see. We're pouring the oil into oven out there. So it should maintain that pouring ability throughout. That's why it is called pour point additive. Right? Okay. And at the same time, you see, it is a machine. If the viscosity is very less and if the viscosity is made very high, it will have the adverse effect in the piston of the engine.
Excuse me, sir.
Okay, so it will have, yes.
Sir, are you changing your slide? Because it's not visible.
I'll change it. Okay, listen, I am talking so many things on the basis of this slide. Okay, keep patience, my dear. Okay, so if the viscosity is changing, then it will have the adverse effect on the engine. So lifetime of the engine will be reduced. So another thing we have to take care is the viscosity. Should be maintained at low temperature as well as high temperature, which is in the scientific term called viscosity index. Higher the viscosity index means at low and high temperature, the differences of the viscosity is very, very less. So whatever the viscosity in Darjeeling, same, almost same would be in the Siliguri, right? So if you can give that kind of additive into the lubricating oil, then what will happen? Yes, it will take care of another properties. It will maintain the viscosity of the oil. So ho gaya na? First one is it is taking care of the flowability and also is taking care of the viscosity of the oil. Right? So what should be the chemistry? The chemistry would be like that. At low temperature, I do not want the polymer to act. I don't want the additive to act. Right? Yes. I'm sorry. At low temperature, I don't want the additive to act. Keep yourself as a simple ball-like things. It should be in a foreign substances into the lubricating oil. But at high temperature, it should act. What way? That polymer should be aligned with the lubricating oil. It should put one more sheet over it. It should put another sheet over it. So what will happen? Sheet after sheet, sheet after sheet. What will happen? It will raise the viscosity of the oil. So at high temperature, your polymer is working. At low temperature, your polymer is not working. So not adding any further viscosity into the oil. But at high temperature, it is adding because of its peculiar properties, because of its design properties, it is adding viscosity into the oil. So what happened? At low temperature and at high temperature, the changes of viscosity will be very, very less. So if you have only one polymer kind of things, giving both the properties, maintaining the flowability of the oil as well as maintaining the viscosity of the oil whenever it is used in engine, then we can consider this. Yes, it is really a multifunctional additive. Is it possible? Yes, my dear. It is nowadays. People are very frequently using, and this is the business of ISO, BPCL, etc. Okay? Right. Now, as I mentioned, this was the earlier vehicles. Right. I mentioned the mileage is 1 kilometer per 20 liter of the oil. Yes, nowadays we can see these are the fuel efficient vehicles and with some additional advantages into it. How? With the help of that work of the research and development unit of so many chemical laboratories. Based on their suggestion only, Hyundai has made this kind of things, Maruti has made this kind of things, Tata has made this kind of things, and so on. So many new have already come up. Right? Yes. Now, if we consider the further thing, multifunctional and biodegradable leaf oil additive, we must go through a literature review. What are the existing ones? Then we can blend our knowledge into it and we can come to a conclusion at the end of the day. This should be my project. Okay? Right. So it should take care of the economy. It should take care of the public health. It should take the environmental protection. Then only these two, yes, will guide us to go for a better kind of lube oil additives or performance additives for the lubricating oil. Is it really possible to develop the biodegradable one? Yes, the answer was there in the year 1893 because of the pioneering work of Rudolf Diesel. He made an iron cylinder with a flywheel at its base, ran on nothing but peanut oil in Germany. Yes, peanut oil দিয়ে উনি চালিয়েছিলেন একটা flywheel. Right. This was the first work on biodegradable lubricating oil. And this was the first biodiesel engine. See, 1893. In remembrance of this breakthrough research, 10th August of every year, we observe as International Biodiesel Day. Right. So the chemistry is very old, 1893, but people could not make its use till 1990. Now we have started doing it. Even our president, yes, Dr. Abul Kalam Azad, he inaugurated the journey of one rail engine, yes, using the biodiesel, right? So this is possible. Now, what is the chemistry behind it? Very simple, I would say. Your chemistry, your molecule should have a non-polar oil soluble tail. As I mentioned, the first thing is it should be oil soluble. Otherwise, no use of it, my dear. And it should have a functional head. This is called the polar head group. Right. It will act as a, yes, Wex crystal network breaker. It can act as a viscosity enhancer at higher temperature. That is the two things. Okay, and some other performances are also there that is not possible to discuss in a hour or so, right? So this is the science behind it. We need to have a oil soluble tail and we need to have a functional head. That is your molecule. That is your molecule. That should be your molecule, right? So olive oil, peanut oil, rice bran oil, and the naturally occurring beta pinene can be of good use for that. If you make the polymer of it, it will be big chain, as you see. People have made it, we have made it rather. Okay, it has polymerizable unit in there, including the biodegradable oils, the natural oil, as well as the beta pinene. Okay, so we can make use of it because they are of that kind. Very silent, only ester functionality is there and the hydrocarbon chain. Okay, with a polymerizable pi centers are there, double bonds are there. So we can think about a big molecule use of it. Similar is the beta pinene. Right. So the idea was the vegetable oil based fine chemicals made environmental friendly additive for olive oil. Obviously, it has the basic skeleton which can take care of the oil solubility, which can take care of viscosity maintenance, and at the same time, it can take care of the performance of wax crystal network inhibitor. Right? So, basically, it is cheap, it is easily available, and contains about 75% of total active unsaturation because we'll do polymerization of it. If it does not have any polymerizable center, then whatever things are there will be of not use for the chemist in the laboratory. So all the things are there in mostly available vegetable oils, right? So you can think about it for a multifunctional and biodegradable, which is also called greener lubricating oil additives, right? Now the fear is to the Didian scientist as well as with us also a high degree of unsaturation in the fatty acid chain of many vegetable oils causes poor thermal and oxidative stability. More number of double bonds, thermal instability because it will get oxidized. That's why it is oxidatively not stable and confines lubricants to a modest range of temperature. Again, the temperature will go beyond 400 degrees, even more than that in other machineries. So, your molecule, if it decomposes at high temperature, then what is the use of using the performance additives? No use. So, we should take care of it also, right? What is the possible solution to improve the necessary thermal and oxidative stability? The triglyceride molecule must be chemically modified before field applications. This can be achieved by polymerizing the vegetable oil. Vegetable oils are there with a good number of, as I mentioned, 75% unsaturation is there. Has to be reduced. How to make them reduced? If I polymerize it, then the polymerization process will take care of will take care of the double bonds. Most of the double bond will get polymerized. So we will be with a very few number of double bond, so that can be taken care of, right? So that's why polymerization is necessary, and that is actually we need it. Unless or until you do polymerization, the oil solubility will be very, very less. So that is needed. Okay. Again, if we can copolymerize with them with suitable monomer, it may induce additional benefits, including biodegradability into the newly formed copolymer. Suppose we may use acrylate chemistry, but acrylate chemistry is not environment friendly. Okay, let us reduce the amount of acrylate and add much more biodegradable kind of things, rice bran oil or soybean oil or sunflower oil into it. Okay, so if we can make it copolymerized, because acrylic acid or its derivative easily polymerizable, and there are good percentage of double bonds in there in any kind of that naturally occurring oils. So if we can polymerize them, not polymerize, copolymerize them, then both of them will combine, and the combining things will have less percentage of acrylic acid, more percentage of the biodegradable things, and at the same time less percentage of the double bond. So it will take care of the biodegradability as well as it will take care of the oxidation stability. So the possible solutions are there exist very nicely, right? So in a gist, we have to prepare the monomer, then it will be polymerized. Then whether we are in the line of making our additives okay or not, characterize them. Try a NMR, thermogravmetric analysis, and viscosity method, right? And then finally, we'll check the goal, whether it is really working or not, the one for which we are working. Is it giving the performance to the lubricating oil as a pore-point depressant, as a viscosity index improver, or as a anti-wear additive? Okay, I'll explain a little bit later part what is anti-wear. Okay, that has to be evaluated in the bench test of getting them in the HPCL, IOCL, or BPCL R&D laboratory. They have their model test engine over there, and the performance will be tested over there. If it passed, then only it can go to the market, otherwise not. Okay, this is that. So the general experimental procedure for the first time is the synthesis of monomer. As I mentioned, you have to prepare the monomer, then it will be polymerized, then it will be characterized, and finally it will be evaluated at their end. So long chain alcohol and acrylic acid. Okay, acrylic acid will be killed by making its acrylate ester. That's why it's that bad activity will go. And when it is making a alkyl acrylate, it is still alive for polymerization, and we can make it homopolymerization in solvent like toluene. The 90 degree centigrade is the decomposition temperature of the initiator. Any kind of polymerization technique needs the initiator. Benzoyl peroxide would be used in that particular case, and in that case, it will be polymerized to polyacrylate. Okay, but acrylate kind of thing is very prone to self polymerization. So hydroquinone has to be added little bit. They are called poison of polymerization. Hydroquinone will be added, followed by toluene and sulfuric acid, because sulfuric acid is the catalyst for, you see, the esterification. So it will make the ester, and finally it will be polymerized with benzoyl peroxide using toluene as a solvent, and then it will be manufactured in the large scale also, the polyacrylate. That will be your polymerizing things. Next point is the characterization. As I mentioned, it will be characterized whether the monomer has really converted into the polymer or not. I here will tell you nicely, quantitatively rather, how much percentage has been converted into the polymer, and same is the for NMR. Qualitatively as well as quantitatively, it can mention considering the carbonyl carbon as a standard, right? Okay. Then thermogravimetric analysis. What is the sustainable temperature for the polymer? Whether it is really applicable to the engine technology, whether it is sustainable in high temperature or not, the TGA data will give you. And finally, the molecular weight, which is also very important to be compatible with the viscosity of the oil. Yes, number average and weight average. Two, gel permeation chromatography, even to the viscometric analysis. Okay, so this is the characterization part. Now the performance evaluation. Yes, our target was to maintain the viscosity throughout, to save the engine technology. Yes. So this is also called viscosity modifier. Will be tested. Then 4-point depression, whether the flowability is there in Siliguri as well as in Darjeeling. Means at low temperature as well as high temperature. That is 4-point depression ability, whether it is there or not. Whether it has got the anti-wear performance or not. What is that anti-wear performance? Any kind of metallic things. If a thin film of oil is not there on the surface, say two balls are moving, if they are coming into the sliding contact, what will happen? They will be in sliding contact or they will be in direct contact. Then if lubrication is not there, it will damage their own surfaces, right? So in that case, the surface will be damaged, the polished will be erased. We say that some wear has formed, তার মধ্যে একটা ফরেন জামা কাপড় এসে গেছে, ভেঙে গেছে, ক্ষয়ে গেছে, that is called wear. But if we add some performance additives into it, what they will do? They will make a film over there. And in that case, if they come into the contact of each other, then that film will take care of that damage. Things will be as good as the initial one. They are called anti-wear additive. ওরা ওই জামা কাপড় পরতে দিচ্ছে না, মানে ওই বলগুলোর উপরে কোনো ড্যামেজ করতে দিচ্ছে না. That's why they are called anti-wear additives. Yes, so that will be tested. My performance additive is showing the viscosity modifier properties, is showing the PPD properties, is showing the anti-wear properties. Yes, first class, this is past the quality control laboratory of IOC, right? Yes, in Faridabad. Fine, then yes, we say goodbye, then it will come to the market, right? Finally, really it is biodegradable? Yes, analyze it. Methods are there. Particularly today, we are using the disk diffusion method and the soil burial test. Okay, if the microorganism eats your polymer, then yes, it is showing biodegradability. So it will be killed after certain years when it is used in the machine. And soil burial test, মাটির সঙ্গে মিশিয়ে দিয়ে ওজন করা হয়, তারপরে এক মাস পরে আবার তুলে নিয়ে ওজন করা হয়, দেখা যাচ্ছে যে শুধু মাটির ওজনটাই আছে, পলিমারের কোনো ওজন নেই. That is called soil burial test. Means polymer has been degraded fully. That's why, yes, we can say it is passed in biodegradability analysis also. So polymerization means the additive is prepared. Whether it is really prepared or not, yes, characterization. Whether it is showing the performances which you desire, yes, nice. Whether in addition to that, it has induced the biodegradability into it, that can also be searched through biodegradability analysis, right? Yes, these are the characteristic spectra. Okay, so you can see that this is the first one is that of the monomer and the second one is that of the polymer. This is the 1H NMR spectra. And this is the 13C NMR spectra of that monomer. Yes, monomer, only one carbon 13 carbonyl is there. When it is copolymerized, you see 2 carbon 13 spectra is there, along with other changes are also there. So you can be assured that yes, copolymer has really formed in the polymerization stages. Then the gel permeation chromatography, GPC, yes, the molecular weight with corresponding polydispersity index. How much is the branching? Okay, less branching is very good. Yes, means it will have more thermal stability. So should be maintained within 2, and you see the molecular weight also is in the desired level of Mn 18,000 to 20,000 and Mw to 33,000 to 32,000 to 37,000, within a good range of oil solubility as well as the compatibility with the performance of the oils, right? TGA data, you see the decomposition temperature is not less than 453 degrees centigrade. So it is nice for the machineries to use it. Okay, with the percent loss is very less at 450 degrees centigrade. Okay, so it is also good for, if it is so, then it is good for thermal stability also. Now the performance evaluations, viscosity modifier, right? The, as I mentioned, the degree of susceptibility of the viscosity of a fluid with rise in temperature variations in quantitatively expressed, which is called viscosity index. If it is so higher value, then yes, it is very good, showing the viscosity at low temperature and high temperature. It is very less differences. Okay, a higher VI value signifies a lesser effect of temperature on the viscosity, which is very good for the engines, right? Yes. The thing is, you see, polymer thickened oil. You see, the first one, the line which is inclined, you see, is not very good, because you see, at high temperature the viscosity is dropping. But the other one, you see, at the high temperature the viscosity is more or less maintaining within a little bit of changes. Okay, so when normal base oil, yes, there is a huge changes in the viscosity at low and high temperature, but when the performance additive is added into it, it is has revised itself, has improved its viscosity property. Low and high temperature, the difference is within the limit of acceptability. Now, how the VM work, as I mentioned, the viscosity modifier should maintain this that laddu shape in low temperature, but it should be elongated at higher temperature to increase the viscosity, because at high temperature every oil lose their viscosity. So if we can add some viscous things into it, yes, if the polymer flattened in the high temperature, then definitely it will raise the viscosity, and that is possible only at higher temperature, and it is impossible in the low temperature. Low temperature polymer will remain as a tight shaped ball only, right? So that way it takes care of the viscosity same more or less at high as well as at low temperature. So this is the beautiful chemistry utilized in the very applied field of the daily use. And it may be of that kind of, which is called asterisk star polymethacrylate polymer. It has, because of its particular structure, maintain that kind of things, which is very good for the viscosity index improver. So this is the plot of which we have prepared too many. Okay, yes, they are showing that, yes, some of them is really showing very good property, right, in the concentration of, right. Okay, হয়ে গেছে সব? ওকে, কংগ্রাচুলেশন, কংগ্রাচুলেশন। হ্যাঁ, করো। ডিগ্রিটাকে এবার কাজে লাগাও, খুব ভালো হবে, আমার আশীর্বাদ রইল। হ্যাঁ, এসো, হ্যাঁ, আর কথা বলতে পারতাম, একটা ক্লাস নিচ্ছে। So this is the additive concentration. You see, very little amount of is showing very good result. ppm level, okay, amount of thing, because one point is there, cost effective. It should be cost effective, then only we can reach to the common people. Yes, right. Next one is 4-point depression in the top hill of Himalaya, right? You see the chemistry very nicely, right? Figure 1, three-dimensional needle-like structure of crystal plates of the lubricating oil, things are there. Okay, উৎপল পরে কথা বলবো, একটা ক্লাস নিচ্ছি, হ্যাঁ, অফিসেই আছি, অফিস থেকেই ক্লাস নিচ্ছি, ঠিক, ওকে। এসে গেল, প্রণাম করে গেল, আশীর্বাদ দিয়ে দিয়েছি, হ্যাঁ, ঠিক, থ্যাংক ইউ, ঠিক ঠিক, কংগ্রাচুলেশন টু ইউ টু। Okay, this is a fine crystal of the lubricating oil, okay, which is the culprit, reducing the flowability of the oil. and it is forming that gel network. Yes, it is stopped the flowability at low temperature. যত টেম্পারেচার নিচে যাবে তত ভালোভাবে এরা কাজ করবে এবং ফ্লোয়েবিলিটিটাকেই বন্ধ করে দেবে। Now what your performance additive is doing? Yes, it is showing its performance. See, these are the things. That black one is the needle shaped crystal present within the lubricating oil, and that kecho type things, yes, is your made polymer, the performance additive. ঢুকে গেছে ভেতরে, গিয়ে ভেঙে দিয়েছে ওদের নেটওয়ার্কটাকে। Right. This is the Popan depression. So once it's able to break the crystal network, then the crystal network will not be able to resist the flowability. Will resist the flowability of the uh, 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 lubricating oil. Right? Yes. So this is the thing. Here things has entered into the crystal network as I shown in the earlier this thing. Okay. So that way we can prevent the zoomage of after lubricating oil. So it will work nicely in the Darjeeling Hill as well as in the plains of Siliguri and all. Right? Yes. So this will be the ultimate result. And these are the things which you have made. That wire-like things is your things. Get them separated nicely. Yes, that's it. So the performance you see is very high. Green one things is the one which is working here nicely. So some of our research work on it I'm showing there with the data. It will also show the anterior performances. You see, as I mentioned, the left-hand side, my left-hand side. This is, it has formed the wear. Damaged হয়ে গেছে sliding contactor জন্য because there was no film in between the metallic parts. So it was without the additives. And the right-hand part is with the additive. See, it is just glowing as it was before. And it is after 10 years or so. It is same, it is showing the glow, right? So this is because of the performance additive. So your machine is saved, right? So that work also done in our laboratory, and we are showing, yes, very good properties we have achieved with the particular kind of things, which is also showing the biodegradability, right? Little bit of chemistry I will mention, because you see, interaction between the iron surface and oxygen of the ester. As I mentioned, the first chemistry was monomer preparation. With whom? The acrylic acid with a long chain alcohol formed one ester. Not acidic, not basic. So not corrodable to the metallic parts. In spite of that, corrode to korche na, in spite of that, the oxygen lone pair is making a function with the iron of the metallic part. It will sit on it through its oxygen lone pair because it was taken deliberately ester. So that's why it is making a fine, thin film on the metallic body. So if the other metal sits on it, it will not have direct contact with the metallic part, right? So the metallic surface will be saved, right? That's why the chemistry working here is the ester molecule, right? So a little bit of chemistry is of huge application in the daily use. Rather, this chemistry is running the world, moving the world from here to there, through railway, through transportation, through air, and through the sea, over the sea. Same that oil is using, right? But what chemistry is working? Very, very basic chemistry is working over there. Biodegradability test. You see, this is after 10 days. Things are there with your additive. Kept it in the incubation chamber 10 days, 20 days, and 30 days. পুরো খেয়ে দিয়েছে. Just see. Yes. Rotten like things. Right. পচবে কখন? যখন এগুলো biodegradable হবে. Right. So it is also verified using the year as well as the GPC analysis. GPC, yes, drastic changes in the molecular weight of that. Yes. Not all the, but some of them are showing nice results. Right? Yes. This is the changes in the molecular weight also, right? And also the biodegradability is still stressed in the other. This was the disk diffusion method. This one is the disk diffusion method, and this is the soil burial degradation test, right? Yes. And finally, IR, if you can observe, yes. See the comparative FTI spectra before and after, right? So you see there is a changes, shift of this particular peak, right? Yes. Okay. So significance and the novelty, what is that? Found to be biodegradable. It is showing better additive performance compared to the commercial additives, reducing environmental pollution obviously as because biodegradability is induced into it, showing multifunctional properties, viscosity index, good. PPT performances is there along with anti-wear performance. So could be an excellent alternative of petroleum-based additive. It is cost-effective formulation of eco-friendly lubricant. Right. So final conclusion is introduction of vegetable oil, the greener part, in polyalkyl acrylate resulted in synergistic effect on additive performance. Synergistic effect means it was some effect. Now addition is raising all the performances. So the effect is not antagonistic, it is synergistic. Thermal stability, yes, of similar kind, increased with the addition of the performance additive. All the core polymers offered I showed you excellent biodegradability if you could prepare them. Much better VM and GWare and 4.2% performance observed in comparison to the homopolymer. Yes, only polyacrylate and this is the homopolymer and this is the copolymer with the rice bran oil or with the soybean oil, etc. Right? Okay, so future work is pending with us. Field trial of the emerging samples. Those who are showing emerging results have to be field trial in the Faridabad R&D of ISC. Performance evaluation and bulk sample to check their potential for commercialization. You know that whatever we do in the laboratory, it should pass the the pilot plant level. In lab, we only make a 1 gram batch or 1 kilo batch. In pilot plant, it will be a 10-ton batch, right? If it passed in the pilot plant, then only it will be shifted to the manufacturing unit where they will take up in a night 100-ton batch. Okay, because trucks will be there, trucks after truck. Okay, it will carry it to the terminals. Okay, so laboratory, then the bulk preparation, which is called the scale up, then it will go to the pilot plant level, and finally it will go to the manufacturing unit of the particular industries. Right? If it passed, then very nicely your product will go into the market. So for that we need the academy industry relationship. Yes, industry should come to us. हमें ये चाहिए, please बना के दीजिए. And our research scientists should also visit to the industry. अब क्या चल रहा है आपका इधर? We have the expertise in it. If you fund us, if you fund our GRF, if you fund some of the instrument, or if you take care of the evaluation part over here there, yes, our brain will help you. Right. That interaction must be there. Otherwise, industry will do according to their choice, and academic research will be purely on academic level. The purpose will not be solved. CSIR, Council of Scientific and Industrial Research. DST, Department of Science and Technology. Yes, always there with the funding agency. Right. So we have to make a good rapport with the industry and vice versa. The industry should have the DSIR certificate. Yes, Department of Scientific and Industrial Research certificate they should have. Otherwise, they cannot run the R&D. Yes, you are getting the DSIR certificate, but you are not doing that kind of basic research in it. Go to the academic institution, take their help, fund them little bit. Yes, একটা GRF minor দিয়ে দাও, will be enough for them. Yes, the project will be taken care by the institute. So that is really needed nowadays. So I must thank to the Lubrizol who has learned me that kind of chemistry. Yes, I'm really grateful today. My 7 year stay over there, yes, really taught me a lot. Not only preparation of that kind of materials, but yes, make us too smart to be compatible with the society need. Yes. Yes, my collaborator, Research and Development Unit of IUC Faridabad. Yes, Gurpreet Singh Kaur, right. My dear student, yes, Mohua, she has developed my that lab over here. Her hand was there in making all the success in this kind of research. My present PhD is around 30 and 15 are from there. Okay, so for that she has contributed a lot for making us successful in doing that additive research. So Mohua is doing good now in Archaeological Survey of India and she is posted in Kolkata. And other researchers of my that group, Liu Weil additive group are there, right? And finally, thankful to DST, thankful to Lubrizol. They're still with me in giving so many engine testing. They have the ETL, engine testing laboratory. So we are running our test with the Lubrizol. My dear friends Arun Panthar, my dear friends Vaishnav, my dear friends NM Desai are there. And finally, Bharat Petroleum and IOC, all are, yes, giving me the base oil. Where from I can get? Yes, it is not sold in the market. I have to get from them only. Yes, they're helping me a lot in giving that particular base oil. Otherwise, our research would have been stopped. Right. And some of our contribution, very recent contribution, important and recent contribution in the live oil additive research. Okay. This is in the this year only. This is in the last year. And this is a short review on that also we have done it because of our research only. And this is the naturally derived green bioadditives. Yes, this is Ectobos. This is the beta-pinene kind of thing, as I mentioned, with the acrylate polymer. Beta-pinene is inducing the biodegradability as well as the other additive performances into it. Right? This is another, the vinyl acetate copolymer, which is showing very good viscosity modifier, pop and depression properties. Right? This is the atom transfer, the new things we have introduced, not radical polymerization. This is atom transfer, radical polymerization with the soybean oil. Okay, so this is available in the website. You can go through and you will come to know what is atom transfer, radical polymerization, which we call ATR. Right? This is with the soybean oil, and this is the chemistry behind it. Yes, this is the tar polymer. Yes, three monomers were there. We could able to do that with the adequate viscosity as well as thermal stability. Right? Yes. This is gone to chemical and engineering data. Right. This is polymer petroleum science and engineering. This is also Taylor and Francis petroleum science and technology. Right. This is Journal of Polymer Research. This is once again. This was with soybean oil. Right. This is sunflower oil. This is with other rice bran oil. Yes. Right. This is acrylate polymers. This biodegradability is not there. Right. This is basically with some wear performances we have added nicely. Right. This is the liquid crystal with the Department of Physics. Yes, Molloy was there. Right. Where is Molloy? Yeah. This is the one liquid crystal. It has gone. I have taken the liquid crystals from Molloy. Professor Molloy does our Department of Physics, and we have done a very good job in it. Yes. Right. These are the things. And finally, thank you so much for your patience hearing. And yes, I'm very fortunate to have so many, around 50 teachers with me to listen the new topics of lubricating chemistry. Okay, and I hope that in future you and you will also encourage your students to do that kind of research in your specific area. Thanks a lot. I'll be very happy if you have any questions to answer.
Thank you, sir. On behalf of UGC, HRDC, NBU, and teacher participant, I would like to thank to Professor Pranab Ghosh for his nice and informative lecture on multifunctional greener materials as performance additives for live oil. I am sure the precious knowledge you gave us about lubricating oil, its needs, its sources and uses, and finally
Thank
research
you.
on it
Thank
uh,
you.
will definitely help us in our studies in
Thank you a
real
lot.
life and in
Thanks a
future.
lot.
Thank you, sir.
Thank you.
Dear participants, if any query regarding this piece, may ask one by one.
স্যার ভালো আছেন স্যার?
হ্যাঁ ভালো আছি। কে বলছো?
স্যার আমি সুজিত।
সুজিত, ও সুজিতকে দেখি দাঁড়া, এটাকে ডাউন করে নেই। Yes, how are you, সুজিত? ভালো আছিস তো? তুই তো এখন
হ্যাঁ ভালো আছি।
টিআইসি। ঠিক। Did you enjoy?
স্যার ওটা তো টিআইসি আমার কমপ্লিট হয়ে গেছে, ওটা গত বছর ছিল স্যার 6 মাস।
ও তোমাদের তো রোটেশন করে দিয়েছে।
রোটেশন হয় স্যার 6 মাস
হ্যাঁ
করে
খুব
হয়।
ভালো, খুব ভালো করেছে। হ্যাঁ ঠিক, সার্ভ করাও হয় প্লাস নিজের কাজেও ক্ষতি হয় না, তাই না?
হ্যাঁ হ্যাঁ স্যার।
আর ও কেমন আছে?
স্যার কমলা ম্যাডাম ভালো আছে?
কমলা রানী, হ্যাঁ ভালো আছে। হ্যাঁ ঠিক, অনেকদিন দেখা হয় না।
হ্যাঁ স্যার।
এখন কে টিআইসি?
এখন স্যার একজন হিলের একজন আছে স্যার, ওই নীলিমা মুক্তান এডুকেশনের। হ্যাঁ ওর বাড়ি স্যার ওই ইয়েতে কার্শিয়াং আছে।
বাহ, ভালোই করছে নিশ্চয়ই। ঠিক
হ্যাঁ স্যার।
ঠিক। কেমন লাগলো আজকের পড়ানোটা? ঠিকঠাক?
খুব ভালো লাগলো স্যার। আমার এর আগে আপনার এই লেকচারটা, এই টাইপের একটা লেকচার শুনছিলাম স্যার, তো তখনও খুব ভালো লাগছিল। পার্টিকুলারলি স্যার ওই যত মানে ঠান্ডা হয়ে যাচ্ছে তত মানে ওই কিছু লুব্রিকেন্ট, ওই পলিমার জাতীয় ওগুলো করছে, অ্যাক্টিভিটি বাড়ছে, ওটা খুব ইন্টারেস্টিং।
দ্যাট ইজ দ্য কেমিস্ট্রি, দ্যাট ইজ দ্য কেমিস্ট্রি। কি বলিস? কেমিস্ট্রি তো এইরকমই বিউটি আছে, ঠিক কি না? ইয়েস
এক্স্যাক্টলি স্যার, এক্স্যাক্টলি
রাইট। ঠিক। আর anybody, if you have any queries, anything, I will be very happy to answer. And if not, okay, then you please go for the other lecture. Okay?
Sanjay, sir, Sanjay.
Sir.
সঞ্জয়, এত চুপচাপ দেখাই হচ্ছে না অনেকদিন
হ্যাঁ
হলো।
স্যার, actually my mother was ill, that is why I can't contact with you.
অনির্বাণ,
স্যার
ও তাই নাকি? মা এখন কেমন আছে?
we have to go for operation actually, that is why
Is it?
actually sir, it's
But is it permissible to her?
I consulted with so many doctors and they said that they will do
possible,
but from our end it will always be risky, and
right.
that is why sir, I can't contact with you. So
I got it. Yes.
Your today's lecture, yes, sir. Sir, your today's lecture is as interesting as always.
Thank you. Thank you.
And I have a small query, sir.
Right. Ask me.
Actually, many
Sir, please mute yourself, sir. Sujit Ghosh, sir.
Different types of additives you are making, and it will be used for in future for the in fuel. But instead of that, it is observing that day by day pollution is increasing in metropolitan city, and not only this, due to the fossil fuel. And my query is that fossil fuel creating pollution, there is no question. But instead of
pollution, yes, vehicular pollution is also there because people are not following the norms. তুমি এখন যাবে কলকাতায়, এখনো হলুদ ট্যাক্সি গুলো ঘুরছে, ওটা কি BS4?
Yes sir,
not at all. কিন্তু টার্মিনালে তো BS4 ভরে দিচ্ছে।
এক্স্যাক্টলি,
টার্মিনালে ওরা তো সেই ইউজ করছে, কারণ টার্মিনাল পুরনো অয়েল বেচে না। বাট স্টিল বেবি বহুত ভেহিকেল আছে, হলুদ ভেহিকেল যেগুলো ক্যাব গুলো তো ঘুরে বেড়াচ্ছে এভরিওয়্যার। 800 মারুতি এখন চলার কথা নয়। তুমি যাও, তুমি নর্থ ইস্টে যাও, সব ছোট ছোট মারুতিগুলো যেগুলো এগুলো সোল্ড হয়ে গেছে এখান থেকে।
দিল্লির অবস্থা,
they are not using the specific fuels, right? This is the reason.
That is
This is the reason.
okay, sir. Okay, thank you, sir.
ভালো থেকো সঞ্জয়, yes.
আমি কন্ট্যাক্ট করবো স্যার, আমার এদিকে একটু প্রবলেম আছে,
No
যে কারণে
problem. ঠিক ঠিক
হ্যাঁ
ঠিক, আমি গেলে দেখা করবো।
ডিসিশনটা ডিসেম্বরেই হবে, ঠিক আছে,
ঠিক।
ওই জন্য একটু দৌড়াদৌড়ি করতে হচ্ছে।
ওকে ওকে,
ঠিক আছে,
স্যার আপনি যে সাইনার্জিস্টিক বললেন, সাইনার্জিস্টিক
Right.
প্রপার্টি দেখাচ্ছে, তো ওটা কি কোনো কারোর সঙ্গে অ্যাডাপ্ট করে না, ইটসেলফ ইট শোজ সাইনার্জিস্টিক এফেক্ট?
It is because of the chemistry. The way it is acting is important. Its acting activity is adding the performance into it. ওই যে ওয়াক্স ক্রিস্টাল গুলোকে ভেঙে দিচ্ছে।
আচ্ছা স্যার।
কি করে? কেমিস্ট্রি করে ভেঙে দিচ্ছে তো।
ইয়েস স্যার।
Right. কেমিস্ট্রি করে ভিতরে ঢুকে দিচ্ছে, because it is also similar of that kind of carbon chain. ওই যে বলে না, রতনে রতন চেনে পরেরটা বলছি না। So it is also similar to that. সেই জন্য ওকে নিয়ে নিচ্ছে, because it is oil soluble and at the same time carbon chain length is also same. So বন্ধু হিসাবে অ্যাকসেপ্ট করেছে, পরে কি হয়েছে, নেটওয়ার্কটাকে বসে ভেঙে দিয়েছে। সো ওয়্যাক্স গুলো আর জমে যাচ্ছে না, অ্যাজ এ হোল কি হচ্ছে, ফ্লোয়েবিলিটিটা থেকে যাচ্ছে। রাইট, সিম্পল কেমিস্ট্রি ইজ ওয়ার্কিং ওভার
ইয়েস স্যার। ওকে
হিয়ার।
স্যার।
রাইট,
স্যার আপনার স্পিচের শেষ লাইনগুলো খুব টাচ করলো, যেটা আপনি ইন্ডাস্ট্রি আর ইন্ডাস্ট্রিকে বলতে চাই।
রাইট, ওইখানেই তো আমরা
আমারও
ল্যাক
কথা
করছি,
আছে অ্যাকচুয়ালি, মানে
আমরা
আমরাও
ল্যাক
বলতে
করছি,
চাই
আমাদের
এটা।
এগিয়ে আসতে হবে, উভয়কেই এগিয়ে আসতে হবে।
ইয়েস স্যার।
রাইট,
থ্যাংক ইউ স্যার।
থ্যাংক ইউ, থ্যাংক ইউ।
Sir, I have one question.
Fine, Animesh, yeah, please.
Yes, sir, Animesh Alda. So you introduced that liquid crystal are actually used for
Right.
lubrication for
Right.
some
Right.
research. So, enlight on that matter. What are the
So you
liquid
see,
crystal
there are
actually
different
used?
kinds of liquid crystals. Okay, some of them are flexible, some of them are oil soluble. So we have chosen from molecular that kind of which has the flexibility. If it is a rigid, will not help us much. Two things were there. It is a liquid crystal, so it has the desired shape within the liquid crystal, so it can enter into the system, and it is oil soluble. So if we can mix it, just blend it with our polymer. Okay, simple blending it. Okay, so in blending, doing the blending, the liquid crystal properties are not getting any damaged. It is showing as such the properties, and with this property inherent into it, we have applied into the lubricating oil, and because of its flexible in nature, so it is taking the polymer, it's taking the other part into the desired pore of desired hole of the lubricating oil. That was there in that liquid crystal. আমি 7 থেকে নিয়েছি, but I have tried at least 70. Okay, but out of them 60 were not found.
Okay, safety answer.
Pardon?
Solubility and structure very important.
Very important. Very important. That's it.
Solubility.
Right. The solubility is also important, as well as its flexibility. That is important. Right.
Thanks.
Okay. Okay.
স্যার।
Yes, Supriya Chatterjee.
স্যার বলছি, হ্যাঁ স্যার, স্যার বলছি আমার একটা কোশ্চেন আছে, যে পেট্রোলের সঙ্গে যে ইথানল এখন মেশানো হয়, এই মেকানিজমটা কিভাবে হয়?
Yes, petrol or ethanol. Means petrol to low carbon containing. Okay, so it has got the this thing calorific value good. Ethanol is also having the calorific value good. Okay, whenever the paraffins, I'm sorry, the this thing, petrol, yes, using, okay, and sometimes some naphthalene kind of things are remaining there as impurity. Okay, but you see, as I mentioned, the chain length is very important. In case of petrol, the chain length is very less within that of C7. Right, so there we cannot use the additives because the chain length is more, so it is not compatible. But if we can use the ethanol, ethanol can do the damage to the wax crystal present over there. It can dissolve the wax crystal over there. Okay, so that way, instead of using the 4-point depressant, which cannot be used because of the chain length of the petrol, ethanol is using over there. That's why it is increasing the cost. This is not cost effective, but we do not have the alternative. Because you see, crude oil varied places to places. It is very much dependent on the geography. It is very much dependent on the altitude. বোম্বে হ্যাঁ ক্রুড অয়েল মিলবে না গুজরাটের সাথে, এত পাশাপাশি। অয়েল ইন্ডিয়া তো অনেক দূরে, ডিব্রুগড়ে যেটা আছে, very widely different. If you see the composition of the crude oils of different places, কোনো দুটোকে তুমি দেখবে না যে আইডেন্টিক্যাল। That's why there is huge scope of additive research. এরকম কোনো ইউনিফাইড অ্যাডিটিভ রিসার্চ এখনো হয়নি, যেটা কিনা বোম্বে হাইকেও অ্যাটেন্ড করতে পারে, অয়েল ইন্ডিয়াকেও অ্যাটেন্ড করতে পারে, আবার গুজরাট রিফাইনারিজকেও অ্যাটেন্ড করতে পারে। নো, ইট ইজ নট পসিবল। It is so widely differences between the crude oils. Right. That's it.
Okay, sir. Thank you, sir.
Yeah, thank you. Okay then. Oh, thank
If
you so
there
much.
is no more-
Okay.
Thank
I
you,
wish
sir.
you all
Thank
the
you,
best in near futures. Thanks a lot. Yeah.
Thank you.
Thank you.
Yes, sir. Thank
Sajal,
you
bye bye.
once again. Thank you.
Yes, sir. Thank you. Thank you for your beautiful lecture and
Thank you. Go ahead with
interaction
the
with
other
the
one.
participants.
Thanks.
Yeah. So we are just about to begin the second lecture, and Professor Paul has already joined with us. So I just request the participants just arrange to introduce him before he starts his lecture.
Okay. Sir, shall I introduce?
Yeah, go ahead.
Hello. Okay. So, welcome, Dr. Asis Pal, UGC HRDC. Dr. Asis Pal is presently working as a scientist staff professor at Institute of Nanoscience and Technology, Mohali, Punjab. He has obtained his PhD in software nanomaterials and hydrogels from Department of Organic Chemistry, Indian Institute of Science, Bangalore, with Santanu Bhattacharya in 2009, and continues his postdoctoral work in Edmund University of Technology with Rent P. Josma and University of Groningen with Netherlands. During his abroad study, he worked mainly in the field of supramolecular polymer for tissue regeneration and dynamic complementary library of self-replicating entities. He started his independent research career with INST in 2015, and he started working on biomimetic material based on his main interest to learn from nature. His research interest includes self-assembled pendant and polymorphic biomaterial, dynamic complementary chemistry, and self-replication, self-healing, and functional nanomaterial, bio-nanocomposite for tissue engineering. He has secured several grants from multiple funding agencies such as DSC, DST, SERP, DPPT, BERT, and UGC DAE. He has published more than 40 very high impact journals in the relevant field. Once again, welcome for this session, sir.
Yeah, thank you for your kind introduction. And at the outset, I would like to, express, the thank to Professor Sajal Das for inviting me to deliver this lecture online more in North Bengal University. So, I mean, what I can say that, I'm giving the first talk in North Bengal University, and it's always very special because I originally belong from North Bengal. So, and, my home, everything is in North Bengal. So then I thought I was really, excited that, I'm giving the first talk in North Bengal University. So as you can see that, so I come from now I Institute, which is situated in the Tri-City region, Chandigarh, Mohali, Panchkula. It is actually in Mohali, Punjab. So these three cities are together, and it's actually the Himalayan foothill that is in a Shivalik range of in that. That's where this beautiful is. This is our main building, what you see, and we have recently moved to this main building 2 years ago, and the institute is autonomous institute under Department of Science and Technology. And this institute is not even a decade old. It was actually from 2013, 1st January we started. So we are actually going to be now 10 years old in a month or so. So what I am basically a chemist, and what I am going to do is that we would like to show you today's talk, and I will keep it rather different. And I would like to show you that how we can expand the horizon. I mean, we can go get away. We can go beyond the traditional covalent chemistry we do, and then we can expand whether can we really go into mimicking nature. Okay, so that's one of the goal I would like to show. And in that regard, before just getting in there, I would like to show again very important thing. I mean, if this institute is state of the art, we have state of the art central instrumentation facility, and also anyone can actually access it and sending these mails cif@inst.ac.in. A few more important thing I would like to show you that we have three basic research unit, which is chemical biology unit, energy environment unit, and quantum material device. Well, you will not get any traditional physics, chemistry, biology. We are very interdisciplinary in nature. So like I am a chemist, but I am actually in chemical biology unit, so I am actually working on various different interdisciplinary aspects. So that's one of the main motto of our institute. So this is Institute of Nanoscience. So we do nanoscience, anything to do with this nanometer regime. I'm going to come there. But then can we really translate that, the science into technology? That's one of the other goal which we have, and then we are pursuing. Now, I mean, this is for the students in case, or the, you can always percolate the information down, is that, we have only intake from the PhD level. For that, you have to have all these national level exam, as you say. Otherwise, we also have this postdoctoral fellow recruitment. Apart from that, we have only internship at the master level. You can actually look at in the we are hiring in the on the website. You can check it, and for the project GRF anyway, for that one can actually write to the individual faculty. Well, so what I'm going to talk to you about this to this lecture is that so first 15 minutes or so, 15-20 minutes, I'm going to talk about three different aspects: why nanoscience is so much important, and how you can actually make nanomaterials, okay, and why what a chemist can do in nanomaterial. It's so how we can actually have such interesting strategies. Second thing is that we would then start, since our title says that we have to really know how to mimic the nature. So we would look at many of the interesting natural example that will excite us always. And then we would try to understand the, mechanism, how nature works. And then what we do is that then I will show at the last, last half an hour, I'm going to show you how at INST or in our group, we are actually making this nanomaterial in order to make in order to mimic the smart nature. Okay, so first of all, what is nano? So I mean, most of us, we would know that nano means very small, and how small it is. So you can think of, this is the earth and this is the football. Typically, if you take the earth and if you make 1 crore pieces of the earth, one such piece is this football. 1 crore piece. So if you take 1 crore football, it will actually have the size of this size of the earth. Now this football we can actually perceive, that this is somewhere in this 0.22 meter, right? That you can perceive, you can see things. But then when you talk about nanometers, so then that means this has to do something with 10 to the power 9 meter. You can see the scale over here. I will just create the pointer options. Yeah, so fullerene is one such nanomaterials which was discovered in 1991 by Ijima. So you can actually look at the typical, the fullerene size. So if you take 100 crore such fullerene, then you can actually get to a football. So you can see these, the relative size between earth, football, and the fullerene. So typically, when in a nanoscience institute, when you talk about nanomaterials, we actually deal with something between 100 to 1 nanometer in that scale size. Okay, so nanomaterial does not mean that it has to always do with the dimension. It can also be with the the time scale. If some phenomena, some natural phenomena are happening in nanoseconds time scale, one can also ascribe that this is a nanoscale phenomena, right? So that's something we understand. And then that's very important. But why it is nano? What we actually get in nano? Because what happens is that when you have a bigger bulk material and you actually break the material and go into very small nano size material, what actually changes is actually your surface to volume ratio. Okay, that is why you can see that what you see a gold, it's a chunk of gold and it looks like a golden color. But the same gold, which is AU, if you actually get it down to nanometer regime, which is something like 4 5 nanometer or 10 nanometer, you can actually have not golden color, rather this kind of red color, or the blue color and all this. Now this color variation in that nanometer regime depends on the size of the gold nanoparticle or the shape of the, whether it's a gold nanoparticle or it is like it's like a gold nanorods or so. So typically, we probably we have studied that how you can make gold nanoparticle is that these are all colloids, right? So you can actually take this gold salt, which is 3 plus, and you can actually reduce this with you can have the sodium citrate, and then you can actually get it reduced to gold colloid, which can be capped with this citrate, and then it will form a stable colloid. And that is what you get to see the gold nanoparticle. And definitely you can, if you look at through TM, you can see very nice gold nanoparticle which are of the diameter. Majorly if you look at take the histogram, then you can see that it is like 14 nanometer or so. Of course, by lowering, so what are the things we learn from here is that we lowering size, we have the surface to volume ratio that is drastically increases, so it becomes more surface phenomena. Of course, there's then another thing comes into picture is the quantum effect, and such kind of nanometer material your classical physics cannot really explain. And what happens is that it actually at that such length scale, it actually start to interact with the light. Okay, now whether these nanomaterials are something completely new, no, it is not. It was there, just that we did not have proper scientific explanation towards it. That's why you can see that in British Museum you have this Lycurgus cup which are kept, which are very nice cup, and you can see this red color cup. Or you can see that if you go to very old Roman Catholic church, you will see very nice such kind of painting, but then it is not actually painting. These are also actually glass window panes, and then you can see that they are very nicely colored. Now what are they? They are actually these gold colloids which are actually impregnated in some matrix. Like in this particular case, it is actually impregnated in the silica matrix, which is nothing but the glass, right? So people knew how to make them, okay, but then they did not know that this is actually in nanometer regime. And you can actually, scientific beginning started in 1857 when Michael Faraday started terming them that okay, these are all gold colloid. Okay, and also another important thing which happened recent year in modern days is that Richard Feynman very exciting lecture, that plenty of room at the bottom. So he actually envisaged in that 1959 that there is something that is going on in the lower dimension, and that has to do with this nanometer regime. So he predicted. And of course, now over the time, we have many of these new microscopy like atomic force microscopy, scanning tunneling microscopy, or TEM. These are the things which actually made the visualize the nanomaterials in a better way. Now also another important thing is that if you look at the trend in last 30 years, and so you see that research on nanomaterials were in a basic stage in before 1990, but after 1990, after we started getting these carbon nanotube, the fullerene and all this, then it started actually growing up. And you can see, if you see, many of the nanotechnology based product are now coming to mass market. So you can see that this has actually given you a lot of opportunity for future growth. and B, whatever. I mean, if you look at many of these information technology, earlier days we used to have this big TVs, right? Cathode ray television and all this. Now you see TV has become very slick, and mostly, you can, whatever your computer used to do, now your phone, the small phone, it can actually do. So why it has become? Because everything has become smaller, and you can actually pack more information in very small dimensions. So everything has become smaller. That is information technology. If you look at the energy, because of course the previous talk was actually talking about this green fuel. So if you look at also the energy scene, I mean, we are also moving from traditional fossil fuel to the solar, or let's say electric vehicle. So there are a lot of things, there are a lot of interesting things which are going on nanomaterials. Of course, on medicines, if you look at the biomarker, like can you really predict if you are going to have, maybe tomorrow I'm going to have a heart attack, can I predict it? Okay. So how you can, so that means you have to really look for some particular biomarker which will get expressed more, in order for you to get some cardiac ailment. So can you really check that in very lower concentration? How is it possible? And that is only possible because of this nanomaterial and their important characteristics of surface to volume ratio, right? So you can actually pack more information on the surface of the nanomaterial so that the detection becomes better. So that's one of the advantage. Of course, consumer goods, if you look at, I mean, you probably would remember that in 1992, first time we were actually watching World Cup on TV, and then World Cup cricket, and then it was happening in let's say in uh, Australia, and you could see that the many of the people, because it was really scorching heat, people were putting some white stuff that was actually nothing but zinc oxide. But then that was a bulk zinc oxide, and people over the year figured out that if you can have a nanostructured zinc oxide, that can actually prevent the UVB or UVC ray, which are harmful for our skin. So of course there are a lot of these consumer goods which were actually present, and you can see these lens, they're actually called photochromatic lens, and there are also a lot of interesting chemistry based nanomaterials which are responsible. So a lot of things we need to learn. And so why, so our institute is the only one institute in entire country which actually focuses on nanotech, nanoscience and technology. Reason being that there are major challenges before us, and this has to do with energy, environment, security, food, disease control. These are different form of these are 5 different major challenge in front of any global economy, or let's say India. And so in our as I said, that we are very interdisciplinary in nature, and then we are looking at in biology, chemistry and physics, we are looking at different aspect, how you can think of nanotherapeutics, or let's say some nanoparticle or nanomaterials for agriculture, which actually gets better. Or we can actually have sensors and diagnostics, or we can have some very interesting strategic materials. All right, so these are things which are our approach. But then if you look at energy, I'm going to discuss now many of these things. Energy, like fossil fuels are limited. How can you improve the renewable energy? So that means you need to have new materials which will act, not only provide alternative source of energy, it will also make way for clean environment, right? Similarly, security is also a concern, because earlier days, maybe you need to have an RDX, and which you need in kilogram. But nowadays you can actually have the explosive which you can actually carry in your bag. But then what you need to do is that such kind of explosive which are actually, let's say, much lower in quantity, that needs to be identified. And how would you identify that? For that, your detection system should be much sensitive. Similarly, food, our space is limited, and we have to improve the crop production. At the same time, we need to also look at that we should not treat the crop with over pesticides and over excessive let's say fertilizer use. Then I think you don't have taste. Secondly is that you are actually putting all these nasty chemicals onto your body, which is also not interesting. So you can improve the crop. At the same time, can you really lower the fertilizer uses? And there's something, there are a lot of things which are hue and cry, which are going on nano fertilizer, and I think it has just got released this year by IFCO. So a lot of interesting things which are going on. Of course, disease control is one of the major area, like the cancer or many other things. Or you are always taking a lot of medicines, right? And the medicines actually also create a lot of side effects. So can we it's like, I am writing a letter. I'm writing a letter someone in Siliguri. I just put a letter, let's say, person X, Siliguri. But then what will happen is that if I post that thing, it will go to Siliguri, but it will never get delivered to that person. But now if I, put an address onto my letter that, okay, I am going to send to Professor Das in NBU chemistry department, Siliguri, and all this, then it will get delivered to you. So that's what happens to the medicines we take. Many of the medicines we take in our body with oral or injection, they actually circulate in our bloodstream entire, the day and all this. And it's then, that residual amount that gets delivered and it works under a therapeutic window. But the problem with that medicines is that they are not, address is not written, that it will be specific to this particular place, it must go there and it acts there. Then your side effects will actually go down. So these are some of the challenges, and this is actually important to really discuss. And I will just show quickly some of the examples. Let's say, talking about energy, how chemistry is important over here. So most of the cases we see these solar cells, and then these solar cells are actually nothing but the silicon solar cells, and they work on these NP, right, and the semiconductor. They're semiconductors, and that's how it happens. But then you can see that the efficiency is hardly 20% or so, and in the lab scale it is 20%, means actually industrial scale will be much lower. But then the problem is that if you have such a solar cell efficiency, that is the reason probably you cannot generate enough electricity that will run, let's say, air conditioning machine or something. At the moment you have solar cells, photovoltaic cell you are putting, and you can only get this fan and light and all these things. So you need to get much bigger area to really produce that much amount of electricity to run a AC, right? The other way of looking thing is that, can we really go away from this, find the alternative which is much more efficient and which can have much more efficient, like silicon solar cell, efficiency is 20%. That means out of 100 photons it finds, 20 photons it is converting into the electricity, right? But similarly, if you can make this, our aim should be that, can you really make it 50% or so? Then what will happen is that in the same area you can actually develop 2.5 times more electricity, right? So that's one of the thing, and a lot of interesting things are coming out. That is, these are all like the multi-junction solar cells and all, which you can actually reach something like 40%. It's already double than the silicon solar cells. But the other issues with this is that these solar cells, yes, you can do, but then they are multi-junction solar cells. In many cases they may not be also stable like silicon towards, let's say, moisture, or let's say oxygen or something like that. So you need to continuously develop materials which are stable and which can protect the solar cells or something like that, right? So there are challenges of that sort. Similarly, if you look at other sources of energy which are going on, like hydrogen as fuel has really come up well, because hydrogen is just H2 as compared to if you talk about petrol. So you have got the butane, pentane, and all these things. Is the hydrogen, the fuel, the high energy density of hydrogen is very high. The only one problem is that hydrogen is highly flammable, and then the storing of hydrogen becomes important. And that, for that, many chemists are actually coming up with certain materials like metal organic framework or so, that will have selective adsorption of the hydrogen, and as and when you require, you can actually pull out the hydrogen and you can use that fuel. And you can see this, there are already train which are running in Germany and India also. There IOCL is going to, IOCL has a plant in Delhi, outskirts of Delhi, and they are also going to, we are going to run hydrogen as fuel as well. Another interesting thing is that if you look at, we are now going big way of the EV charging station, right? Many of the electric vehicles are already in Chandigarh. All the, buses are now going to be electric, and already we see that 50% are electric vehicle. But what you need is that EV charging station. But another important thing one has to also remember, that such things is that, you go to now petrol pump and you actually ask for 1,000 rupee petrol and you get the petrol very easily, and then you are done and you can drive off. But then what happens, the EV, if the EV charging takes really long time, like overnight you are charging the bus, then it's rather not so convenient, right? So what you need to do is that you need to have charging which should be very fast. And for that, I think people are working on very interesting exponential chargeable super capacitor, and these are some of the very active area. And then if you can really make materials, which are nanomaterials rather, which can charge fast. Like, if whatever you are doing overnight, if that can happen in 30 minutes or so, then you can just charge it and then you can again drive off. That's another thing. So another interesting thing is that alternative source of energy is piezoelectricity, right? You always charge your mobile, right? And then you have to use these, the coal-based electricity and all. Can you really think of that when you are going for jogging and then you put this phone, and then what happens is that as soon as you put this phone, the phone gets you go for jogging, and then phone gets charged automatically, right? So the piezoelectricity is one such thing that you can have some piezo responsive material, and as you actually do some mechanical agitation, or you are running, so that mechanical energy will actually get converted into electrical energy. So that is actually the piezoelectricity. So then these are some of the things many of the INST scientists we are working. I will talk about it when we discuss about what we work on. Another very interesting thing is this nanoparticle mediated drug delivery. As just like that, what I said, when you have in healthy cells, and when you have tumor cells, there are some basic features which are different. These are all actually cancer cells, or all you can have interstitial intercellular space which are more. It can have little bit of pH which are different, which are little acidic pH. If you can make your nanoparticle where you are putting your drug molecule, the two things which can happen is that even you can actually, using your nanoparticle, you can carry your hydrophobic drug also in your bloodstream, and you can actually go and deliver the drug. You can see that you can also have you can have injection mode, or you can have an oral delivery which will come, and it will go. And then you see, if you can make your nanoparticle magnetic and you apply some magnetic field, it will go and deliver the drug exactly in that without any side effect. So these are the kind of things one are looking at when you talk about nanomaterials. But then, now these are things which people are doing. But then if you look at the nature, now this is one of the things which I wanted to discuss today, is that if you look at the natural world, and you will see that in natural world you have the ant, you can see, right? You cannot see a red blood cells, because then you need to look at through the light same way, but then you need to have this objective lens so that you can look at it. But actual nanomaterial, if you talk about, that is actually DNA, which is like 2-3 nanometer or so. But the DNA you cannot actually look at through your normal microscope, optical microscope. For that, what you need to do is that, similarly, you can also have this man-made, let's say, the carbon nanotube is one such thing, which are actually compared to this DNA. But the problem is that such nanomaterials are very difficult to see for you. And then mm, for that, what you need to use is that you need to use something called electron microscope. That's because optical microscope is limited, because you are using visible light, and through visible light you cannot really now. What is the wavelength of visible light? Visible light wavelength is something between 400 to, let's say, 700 nanometer, right? And now if you want to see something which is like 5 nanometer or so, definitely this light wavelength is such that it will not be able to show you everything. For that, what you need to do is that if you want to have 5 nanometer object, then you have to have the light source where the wavelength will be much smaller than that. An electron, as you know, that de Broglie's principle of wave particle duality, electron is nothing but a wave, or it's a particle. So, right. So you can use this electron microscope electron, and you can actually visualize this, any of this nanomaterial. Now, once this electron microscope came into the picture, then that was in early 2000 or so. Then people started looking at very interesting phenomena, like that we all know that the leaves are always green, right? And why we know that? Because we know that, yeah, leaves has got chlorophyll, and that has got chloroplast has got chlorophyll, and the chlorophyll is the pigment, and that it actually absorb everything other than green, and it actually green comes to our eyes, and you see. Similarly, you have this carrot where carotenoid, and then anthocyanin, you actually have these compounds. So it actually absorb anything other than that particular thing, that particular wavelength, and it actually comes to our eyes, and we see that color. That's how we actually perceive the color. But then when you looked into the butterfly, let's say, and then we see that the butterflies are so interesting color, very very interesting color. People try to look at, so what you do is that you kill the butterfly, take the fins, and then you try to extract in a solvent and try to isolate the pigment, just like the natural product chemists they do. And then you try to look at, and you don't see that, you don't see so many colors, so you don't see the corresponding pigments in butterfly this thing. So scientists were really puzzled that, okay, how come there's so many colors, but we don't get the pigment. But then after the advent of this electron microscope, when we started looking the fins into it, and you can see that, in the fins, if you look at more, you can zoom more, you can see that eventually the fins is this, these air pockets, which are very nicely periodically organized. Okay, so very nice, you have these fins, that is the material, and you have this air pocket, and these are periodic in nature. Now if you remember that your class 7, that experiment, that you have a bucket of water and you have a stick, and what you do is that you put the stick in the bucket, then what happens? The stick appear bent, right? Why? Because you know that water has a refractive index which is 1.5, air has 1, so there is a refraction which is happening, right? Now same thing happens also here, but then another interesting thing is that it not only happens once, it happens multiple times, because you have created, or you have in butterfly wings, fins, you have multiple such things. So multiple time refraction happens, and this phenomena, and what you get is something called net reflectance, and that is how you can actually generate color. That is actually a very interesting observance, and from there different new research field got created, based on this nanoscale manipulation, is called photonics. This is very interesting field, and it's really coming up. It's all has to do with the interaction with the material, with the light, and then this photonics. So seeing this, the scientists also started developing very interesting such kind of layered material, where you can have actually multiple different refractive index, and can you really play around, and can you really create color? Okay, can you really create color? So this is one of the things people are working, and this has only come after this Engwon the chemic paper by a Japanese group in 2003. So one mystery got solved. Now other things which we always know, that if you look at your lotus leaves, and if you throw water into it, not only lotus leaf, you can also have the colocasia leaf, that's like your kochupata. So you can actually put some water onto it, and you see that water does not really smear like this. Water actually take a shape of a football. And why is it so? Many times, in our class 10th, and we we were told that it is like an waxy solid, there is something is waxy, that's why you get to have that. But then what is that wax? Can you really have a look? Then when you look at through again microscope, electron microscope, we can see that there are all these periodic small protrusion over here, you can see. And because of that, what happens is that the water droplets actually because of that, things become actually hydrophobic. That's why the water droplet, they try to minimize the contact angle, and with the surface. And that is the reason, if you look at, if you measure the contact angle will be something like 160-degree. This is a very high contact angle. That is actually characteristics of super hydrophobic surface. Typical surface, if you take, it will be actually less than 90, which are like hydrophilic surface and all this. Now this is very interesting, and one of the very interesting thing you see in lotus leaf, and the lotus leaf does not have any dirt. Because if there is dirt onto lotus leaf and then there is rain, then what happens is that all the dirt actually get washed away by this particular football. And you can see this example, that in any dirt, then actually water droplets actually takes it away. Now scientists, when we look at through the lotus effect, then we found that that's actually very interesting, because if you can have a very nice pattern nanostructure like this lotus leaf, then you can actually make the surface super hydrophobic. And then what can happen is that you can make this self cleaning. So anything you make, your textile or your shirt, you don't need to really wash it, and that's what happens. And then you can see that people came up with this shirt where you can actually have this nano patterning, and you can actually have, just like typical shirt will not give you this kind of signature. You can see that that flying machine also came with the jeans. Now this is important, because these are all self cleaning technology. And why it is important? Because now you might think that you have in North Bengal, you have got Tista, Mahananda, everything is there, you can have enough water, you can actually wash them. But there are many places, I mean, let's say you go to Rajasthan desert and all these things, you might not get water. And let's say our BSF Jawan and all army, they are all standing there, and they need to wash their clothes, right? Can you really make the clothes self cleaning, that it does not really need to get washed? So there is also something called it. So basically our dirt comes because of this, the dust in the air, or it can be due to the to these microbes, which actually, stays in our body and it actually attacks your shirt or pants. So can you really put some antimicrobial agent impregnated on this? And then people came up with something called TiO2 nanoparticle, which are photocatalyst. So TiO2 nanoparticle, if you shine with sunlight, then they get active and they actually kill all the microbes. So then the scientists came up with this very nice self-cleaning textile, but then you have this nano finishing with TiO2 nanoparticle. So what you have to do is that you come home and put this onto sunlight. You don't need to clean it, it will automatically get the cleaned. Or if you want to clean, you can just spray with little bit of water. You don't need to really dip it into water, because that much water may not be available in places like in Rajasthan, or if you want to go to Siachen glacier. So these are all actually very, very interesting thing, and you can see that as a chemist or nanochemist how you can actually do. Nature has many more interesting example. You can see the water spider, they can actually walk on the water, you cannot do. That's because that if you look at this toe, and then you can see that you have got this micro hair, and they have a lot of branching, and they actually trap a lot of air that actually help in the buoyancy factor, and that's why they don't actually dip. And if you look at from beetle to fly to, let's say, the gecko, you can actually look at their toe and the nanostructure in the toe, if you look at from the electron microscopy. And that is the reason scientists thought that it's very nice, because the spider, this is actually a very interesting thing, because this is how Spider-Man probably can actually if you have the palm like that, you can actually stick to the surface and actually you can go. And this is actually gives rise to this concept of adhesive. If you can have this pattern nanostructure, you can probably create very interesting sticky note. I think all of this sticky note you must be using it. So that's how if you have this nano patterning, you can have very nice this adhesive creation. So people are working on it, such kind of very interesting. Even we are also working on such kind of interesting adhesive. And uh, so I think, having given this couple of examples, and I just want to give one or two more examples and get to the actual work, what we are doing. So many of the Hollywood movies, if you look at, and many of the very famous writer, like if you must be reading this mm, uh, the famous writer Yul Verne. So he has written, let's say, this movie you must watch. There's something called Journey to the Center of Earth, where you can see that this Brandon Fraser, they will be going into these very under volcano. They will actually reach the journey to the center of Earth, and you will see many of the historical places like dinosaurs and many things you will find. And you can see these rocks. These rocks are floating in nature. How a rock can float? So it is only possible under some magnetic field, right? And if you look at now, this is very interesting. And if you look at the inspiration, and that's what people are working. And if you look at any diamagnetic material, or let's say superconducting material, you see they will actually repel. You see, this is the diamagnetic material, and if you take a magnet, what it will do, it will actually paramagnetic material, it will actually take it like that. But if you take a diamagnetic material, it will repel and it will stay like that. And that's what actually is the basic principle of this maglev train, which are like the bullet train in Japan, China, and many other places. So there your wheel does not really touch, right? And it does not touch the, let's say, the railway track. There is always a gap, and that they are actually magnetically levitated. And for that, we need to, that is actually gives that propulsion, and that is why there is no frictional element, and your train can move 600 kilometers per hour. That's the reason magnetically levitated trains are important. But reason why I'm saying, and I'm going to give you that inspiration, is that for that you need to have this superconducting material, which you need to actually put in the train. Now the problem with India is that our most of the superconducting materials what are available, for that you need to use actually liquid helium and all these, and they are, you need to really cool it down very low temperature. Okay, so that's one of the problem. But in hot country like India, such kind of thing, you need to have room temperature superconductivity. That is very important. And one of the research, and again the chemists are involved, and they are actually making, is that room temperature superconductivity. And I think there are some breakthrough by one of my junior actually in ISC. So they are working on this kind of thing. That's very important, because if you want to really run such kind of magnetically levitated train at lower cost is important, then you must have such kind of room temperature superconductivity, right? I hope I have given you that thing. And these rocks, if you look at, if you watch this movie, you will actually understand the concept of it. Now there is also another very interesting thing, as I was saying, this Harry Potter movie, if you know, that some of the inspiration is that Harry Potter has this gown which you call is that cloak. Okay, and now if you put that gown on, and you can see that you go completely invisible. And that means this concept actually gave us the idea of metamaterials. Can you really have something like metamaterial, which are very important for defense and all this? You can actually camouflage yourselves, and then you can tweak the light, so you can actually have these metamaterials which you can devise, which will actually interact with the light such a way that it will actually tell the light to go some other pathway, and then you will not light through that light, you will not be able to see. And you can see that Mercedes company has already come with such kind of invisible car. Okay, and you see people, this is in 2006 already in metamaterial based thing, so people are wearing this gown and you can actually see this car backside. Now all that it has to do, and I am just again reiterating it, is that you need to make material. Normally we know there's water, you see that stick you have put, and this appears bent, and normally you see this water has a refractive index is 1.33 or so, that is why it appears bent. Now can you make material where you can have the refractive index of the water? If you mix the material in water, that will actually become minus refract. Can you make it minus 1.33? Is it possible? It sounds weird, but I think if it is possible, and if you actually mix them two, then what can happen is that you can actually match the refractive index of the air, and that's how you can actually fool people and you can go invisible. So these are very interesting things which are actually going on, and I thought that these are important things which I need to say, that where science is going. And of course chemists, physicists, biologists, everyone has role in such advancement. And one of the role model now for chemists, now being in a chemistry department and I'm being also chemist, one of the very important thing to access the nanomaterial is that, see, if you have a bulk material and if you keep on breaking the material, eventually you will go to the nanometer dimension. That is something called top down approach, right? You have to go for breaking method. But then we can also think of, we have our covalent molecule and all. Can we really assemble the molecule? And if you assemble a couple of molecules together, you can actually make bigger molecule. Then what will happen? The size will increase, right? That's a new chemistry which has come now, that is called supramolecular chemistry, and I think all of you must be knowing about it. Look at this. Richard Feynman in 1959, he talked about that there is a plenty of room at the bottom, right? That's the thing he said. That means something he dictated about nanotechnology in long time ago. But then after almost 60 years later, something called nano car came, and then I know this very well because this particular material was made in Bernard Feringer's lab when I was in Groningen. So his Feringer's office was just one office away from me, and they were that time in 2012 they made this, and they were struggling with it because they wanted to make a nano car. So where you shine some light and there will be some cis trans isomerization, and this will move and the entire car will move. So they were really struggling for almost 10 years, and eventually they made it. Similarly, Stoddart and Jean-Pierre Sauvage, they come up with something called molecular lift, which is basically based on host gas complexation molecule. So you can think of that, this person takes the lift and then he goes away. This is something called nano lift, and that actually gave them this Nobel Prize in 2016. All right, so this is very important, and you can think, and I will tell you why it is important, because you can consider that I can tell you this also at the moment, is that the implication of this Nobel Prize is that, suppose we are always talking about drug delivery, right? Nanoparticle based drug delivery and all. Now maybe 10 years down the line it can be like that your drug will be attached to this nano car, and this nano car will be injected in your body. It will go and it knows exactly where to go in your body. It will go to the tumor and it will deliver your drug and it will come out of your body. So that will be something called intelligent drug delivery vehicle, right? That's a direction or goal these guys are actually now working on it, right? So as a chemist, definitely we like a bottom-up approach where you can take molecules. So basically we know that covalent chemistry, so you take these two molecules, you do covalent chemistry to make this molecule. But then that's where we don't stop. We take 2-3 more building block and we take them together. Because of supramolecular chemistry, we can actually make bigger molecule, and supramolecular chemistry involves non-covalent interaction like hydrogen bonding, host gas interactions, right? All these different things. And that's how you can actually, from molecule, you can actually have the supramolecular aggregate. And if your molecule you are dealing with, they are actually biomolecule, you can actually go for biological intelligence, or you can actually create cellular life. Many of these things which I'm going to discuss today, in a short while. So now that I have told you and gave you all the inspiration why it is important to mimic nature, what I'm going to run you through is that now I think I have 15-20 minutes. So this 15-20 minutes, I'm going to quickly run you through different kind of work we do. I think it may, if it is too heavy, that's okay. You can just sit back and relax. But then I don't want to really go much in details, because then it will be too much for that. So basically in our group, we are chemists, but in our group, we have not only chemists, we have this biophysicists, biologists, pharmacologists, theoretician, everyone, we work together in a group, okay, in INST Mohali. And one of the few groups which I work on, one is this polymeric material. So where we see the protein is nothing but a polymer, right? So now what it does is that it nicely fold into some conformation, and actually many of the enzyme, they perform their job, right? Is their duty to perform. So we thought that, can we really mimic such kind of protein folding using some synthetic polymer chain? So that's what one of the goal we do is that, you take the polymer chain, we apply some stimuli, and then under the stimuli, it actually goes into single chain polymeric nanoparticle. Now what happens, what is the benefit of having it? Because if you make such kind of single chain nanoparticle, their size becomes very uniform, and if your size is uniform, the amount of drug, if you want to use for drug loading delivery, drug loading, that will be also uniform. The drug release will also be uniform, and if the drug release is uniform, then uh, then what happens is that you can have a sustained release. Similarly, using such kind of polymer, you can also create network polymer, which are stimuli responsive, and you can actually create very nice self-filling coating surface. So we are working on very interesting, different things. We are working also on chiro-optical polymers for these, chiral photonics, or making people invisible, such kind of things. Uh, and these are the group people who are working, and many of them are actually moving to US, and we are having collaboration over there. Apart from that, one of the main research area where we have published in last 4-5 years a lot of interesting and very high impact paper, all in SES, is so what we do is that we take peptide material, and we said that, look, protein is a very big molecule. Can you really take the functional minimalistic building block of protein, that is peptide, and can we perform some self assembly, that is nothing but a supramolecular chemistry with non-covalent interaction, and get some nanostructured material, like you can see that these are all nanofiber, and we can cross-link them to form hydrogels. Okay, and these are actually very useful, because this hydrogel you can actually use for drug delivery. We are also looking at peptide bioelectronics. So like, can you really have this peptide material, which are biomolecules, to create your piezoelectric behavior? That means with mechanical strength, it will already generate electricity, which is good. I will come to that very interesting example. The third major active area which we are working on, that is actually, since we are working in India, and we are one of the very chosen group, where working on polymeric material, classical polymer, and also the peptide based material, we thought, okay, can we really marry these two field and make this peptide polymer conjugate? And is this conjugate, when we made last 2-3 years, we are working on it, and we see that we can actually develop very interesting extracellular metrics for mimicking those kind of hydrogel. Actually, you can do bone tissue engineering, we can do cardiac, heart, muscle tissue engineering, a lot of interesting things. So apart from that, we are also working on these polymer materials, which we are using for, I have a project. So we are going to Rajasthan, and we are trying to do agriculture in Rajasthan soil, because we have this polymer hydrogels, which will actually do drip irrigation, just like in Israel we do. So you don't need to really use a lot of water, because already India is a water scarce country. So we are minimizing the water uses, and trying to really provide drip irrigation technology to this desert area. So these are different area we are working on. And so main focus, as I earlier also said, that our focus is to mimic nature. And if you look at this, if you make a cut on the tree surface, what tree does is that it secret latex, so that it actually protects against some antimicrobial or attack, right? Similarly, if you look at our body is a very nice, if you make a cut in your body, it automatically heals, right? If the cut is big, then definitely you need some other treatment and all this. You need stitching and all. Otherwise, it actually, the body is also very natural and it actually does. Look at now nature. There is another important control. You see that precision control. You see the ice crystal. They are very precise. Look at the honeycomb structure. They are also very precise, right? But when we try to make some nanostructure in the lab, we cannot really make it. There is a problem. But then you look at this, this chameleon changes its color. How it changes its color? It actually does some muscle actuation. It changes some muscle parameter, and then it changes its color, and it can camouflage itself against external attack. Similarly, if you look at our cardiac heart muscles, that is always pumping in our body. So normally, if you look at your toothpaste, if you press the toothpaste, what happens is that that paste comes out, right? So if you apply force, it actually flows. But in the cardiac heart muscles and all this exactly happened little different way, and this is very interesting. That is called strain stiffening material. So if it apply force, it actually resists, and that is why your body, many of these your blood vessels and all this, they don't rupture, and they are carrying and they are continuing to do work. So this is very important, and these are very interesting, fascinating different dimension to how to mimic it. Okay, and in our lab, this is what we do. We try to mimic them. We try looking at the nature, and we say, wow, that's very nice. But then we ask the question, but how can we really do it? So having this, so we thought that, okay, can we really have this mimic? So as I said, these are all stimuli responsive, and this has to do all with this this supramolecular non-covalent interaction. We thought, okay, if we have self-folding of protein, can we now make material? So this is exactly the thing. We can make now synthetic single chain polymer, and we can apply some stimuli, let's say light or something else. It can actually fold, and it can fold into some, it depends. If you are doing at very low concentration, it can fold into globular nanoparticle. If you're doing at higher concentration, it can actually form very nice network structure. And one of the functional unit you might take, and we showed that we took, that is actually coumarin unit. Coumarin is very biocompatible. It is there also in lavender tree. So we took that, and coumarin is very good because you can actually have this 2+2 cyclo addition to form the cyclobutane adduct, and that can be done at 320 nanometer. But then if you use other UV length, that is 254 nanometer, this actually ring opens. So you can selectively create a hierarchical structure. You can also open it. So that's very dynamic. So this is also a dynamic covalent chemistry. Okay, so I don't want to go into much details in showing the polymers. So this is the polymer where we actually do all these things. Now what happens is that when you are conjugating it, the polymer TG value, that is very important parameter for the flow property of the polymer, that also changes. So with this, I just wanted to show you that what we showed is that now if you take the polymer and coat it on some surface, so very nice coating, and you make a cut on the surface, based on the temperature or the light you provide, you can actually heal the surface just like that. Just like we make a cut in our body and it heals, these are also intelligent material. It can also heal the surface. Okay, and we showed that also that this is possible in the, not only in the case of coumarin, it is possible also in the case of thymine. And that's what we shown that. And not only that we are doing in the lab with the light, we also showed that in the presence of sunlight or solar simulator, that okay, you made a cut over here and it can automatically self-healing. Why am I saying it? You remember that when I was talking about energy in the beginning, I was saying that many of the silicon solar cell is going to be replaced with, let's say, perovskite solar cells, and perovskite solar cells are actually that way not that good in terms of stability to air or moisture and all this, right? And suppose there is an acid rain, then what will happen? Or you have put this photovoltaic cell, a bird comes and it does some shit, and bird shit has this phosphoric acid, and that will actually reduce the the solar cell efficiency. Then what you need to do is that you need to put a very nice coating. Now if the bird comes and with his claws, if it does scratching, that will also automatically get healed, as you see over here. Not only that, it will also prevent the penetration of oxygen or moisture onto the perovskite cell, and it will actually give you better performance and longevity, right? So this is very important, and they will actually do. Seeing this, I think I am talking to also another company in Bombay. They actually want us that, okay, can we really take such polymer film and put it onto the refinery, which is in the middle of the sea. That is very important, because every time they have to go and do a painting, that's really like in the middle of the sea. It's very difficult because a lot of sea the weather is such that they get corroded. So can we really prevent anti-corrosion material? So this is one of the area which we are working on based on polymer. So having done that, now this is another interesting story. This is little biology oriented. So this actually I got inspiration looking at my son in 2019, that he got typhoid. And then in typhoid, what happens is he was just a 5-year-old boy, so that those days. And then in typhoid, what happens is that you get very sharp shooting of your temperature in the body. Fever shoots up in 104 or something like that within a minute or so. And then the kids, they cannot also say that I'm having fever or something like that, so you have to administer medicine. Every time you apply paracetamol, it will actually get it down, and then that's how it goes, right? So we thought, now when I was treating him, then I was thinking that, okay, can we really have something that we take a nanoparticle and we put the drug into it, and we take that nanoparticle and the drug, and it will circulate. Normally it circulates in the bloodstream, and if the idea is that if the nanoparticle is very small, then what will happen? It will not get excreted from your body faster. It will actually circulate a longer time. And now what happens is that if you now have your fever, which is coming up, so if this nanoparticle can sense that, yeah, fever is shooting up, and if it release the drug just like that, only then it will be very nice, excellent material. So based on that concept, and this is something called maintaining homeostasis. So we thought, okay, we made a polymer chain, and then polymer chain, we can actually put the drug into it, and can we really release it? Now, one of the thing is that small means how small? It should be less than 30 nanometer. And if you can have materials which are less than 30 nanometer, which is good, because then, many of the cases, like you have brain tumor or you have something in the eyes, you cannot actually deliver medicines over there. The one of the reason being is that, your blood-brain barrier or blood retinal membrane, they actually excrete all kind of drug. Now, you can actually fool them if you have nanomaterials which are less than 30 nanometer, because then only you can actually cross such kind of blood-brain barrier. And so we made such nanoparticle, and we actually put a polymer which is thermoresponsive polymer. If you go more than, let's say, 37 degrees Celsius, then it will sense and it will actually throw the drug, right? And this is the story of the drug, that it can actually, 37 degree, it will actually start to release it. And this is something to do with the LCST behavior. I'm not going to go in details. And we showed that, we can have very nice small nanoparticle, which are 16, 17 nanometer nanoparticle, and we can do detailed study. I don't want to show you. But then most importantly, you can actually put some kind of antipyretic drug like ibuprofen or so, and you can see that you have a very sustained release of the drug over the time at body temperature, which is 37 degree. But as soon as the temperature actually goes a little higher, then you can actually start to have this, release. And this was a proof of concept we showed. So that means you don't need to really take medicines multiple times. You take only once, the medicines will do the job for you for at least 2-3 days. So that's one of the things we are looking at. We are now going for details animal study and all to validate these particular things. All right. So we have done that. And so this is very interesting work, and we are just working on it. We have 2-3 very interesting thing, and we have a collaboration with the broad. Exactly this thing I was talking about, that, how you can actually make yourself, use of these chiral photonics, so that you can actually make something very nice, metamaterials or so. So we are actually now making very interesting polydiacylene based materials, which I have been working on for a long time. So then you can see that is a transparent film. You just shine light, UV light, for only even 30 seconds. You will see that from transparent, you will actually have a magic. You will have this red color. And this is important because this, if you can put chiral molecule, chirality, right? All of you studied organic chemistry. What is chirality? So if you put a chiral molecule and they are opposite chiral molecule, you can actually play around with, and you can do very nice circular dichroism spectroscopy to find out this kind of opposite chirality. And not only that, if you can put such gold nanoparticle, which I just showed earlier, they can have a selection, and then you can amplify your signal. This is very important for amplification of signal, because this is where you actually create nonlinear, optical optics, and then you can also, go towards these metamaterials or left-handed materials also. I'm not going to discuss more in details, but I think maybe sometime later when we talk about it, I can talk about it in details. Well, so having said many of these polymer things, one of the thing is, I'm just coming back to, is that how to mimic the nature. And this is very important. And if you want to mimic nature, self-assembly is very important, and self-assembly is one of the very key for origin of life. And I have been working on it since my days in Netherlands, that how we, nucleoside, RNA chemistry, many of these things got created, and eventually they kind of self-assemble. And not only that, they self-assemble very fast. Okay, this is very important because I showed you that honeycomb structure or the ice crystal like structure. Why we cannot make it? That reason being is that most of the self-assembly we perform in the lab, they are actually driven by the equilibrium thermodynamics. But nature is very smart. They always do non-equilibrium self-assembly, and that they are kinetically controlled. Okay, so that is the basic difference. And our idea was that, can we really have kinetically controlled product? And for that, we actually got inspiration from this amyloid self-assembly. What are amyloids? There are these Alzheimer disease, Parkinson disease, and all this. What happens in that? In our brain, there are certain, let's say, peptides or proteins. They actually form some self-assembly which are misfolded. Okay, you cannot really cure them, and that happens very fast. And once it start to degrade, your brain start to degrade, and you actually tend to forget things. But then we took inspiration from such kind of misfolded protein, and we thought, okay, can we really take the nucleating code of the protein and start doing some nucleation driven growth? So that means you need to form a nucleation, and then eventually they will do some elongation. So with that, we tried doing some very interesting small peptide mimic, and we see that this peptide, it can actually form, you vary the temperature of the solvent composition, you can actually have nanoparticle or nano fiber or very nice twister driven nanoparticle. So you can actually create the kind of structure you want. Okay, now this is very important, and we thought, okay, can we now do more? Because okay, we have control in the one dimension, you can have a very nice control. Can we now control over two dimension? So we then what we did is that we changed this n terminus and with again the Kumarin unit, because Kumarin unit can do this 2 plus 2 cycloaddition, as I said. And you can actually form very nice, not only nanoparticle, nanofiber, you can also form sheet like structures, and you can actually see the sheets are actually very thin in color, and you can actually visualize also from confocal. So these are very interesting material and peptide materials we dealt with, that we can actually self-assemble molecule to form nanostructure. But why they are important? And this is important because you see, as I said, that life, how it got created is that it's self-assemble and it forms some compartment, right? And then when you talk about us, we are a multicellular organism. Amoeba was actually unicellular, right? And couple of things, can we really dictate the molecules? Like Louis Pasteur, what he did is that he actually looked in microscope and he actually separated the enantiomer of sodium ammonium tartrate. Okay, you separated it. But then we thought, okay, can we now make molecules which are little chiral in nature? The peptides are D-chirality or L-chirality, and you throw them in the solution. Can they self-assemble completely different way? Some of them will go this way, some of them will go this way. Just like in your class, you have many students who are coming, and some are coming from, let's say, Siliguri, some are coming from Malda, some are coming from Balurghat. Then what happens? Initial days they are together. Then after that, you see that Malda people are going together. Okay, they are close. Some people, Balurghat people are going together. Maybe Darjeeling people are going together. This is something called self-sorting. Can we really self-sort? And this is how intelligent nature, they actually form the compartments, and that is one of the thing. And we also show with our molecule that yes, you can mimic such kind of things with the compartments. And we can, not only that, one of the very important thing what we did recently, and that is that you can visualize these individual these fibers with, let's say, some dye. You can actually use super resolution microscope to see that is the blue color, sorry, green color or red color, and you can actually visualize that they are actually self-sorted. You can see that there is no correlation between them. Such thing you can do. But then what is the idea was that we had big protein, and we thought that okay, we'll take a minimalistic model of protein, and which is nothing but a peptide. Now the problem with that, all these enzymes are actually protein, right? And if you heat these proteins, they actually lose their activity, right? Enzymes do lose their activity. We thought that, can we now mimic this as with a biocatalyst with this minimalistic model of the peptide, and we put some functional unit like histidine as the amino acid. And as you know, histidine is actually very important for these chymotrypsin enzymes which are there in catalytic triad. So we then, with this, we tried doing this hydrolytic cleavage catalysis and all these things, and we could see that we can actually have very nice control over that. So this is something called catalytic amyloid, and not only that, it can actually perform at much higher temperature. So it is actually better than the natural material. You can actually have better biocatalyst than the enzyme as well, right? Similarly, I just wanted to tell you this, that you can also do some structural manipulation, and you can actually form play between self assembly and disassembly. And the important thing is that if you have self assembly and disassembly, you can actually play with the dipolar polarization and all this, and you can, and because of that, if you now record these materials becomes piezo responsive. And you know that piezo response, I said that if you put your material on the surface of ITO coated surface and you tap your finger like that, that means you are giving some mechanical energy, it will actually give you some electrical energy. So you can actually create peptide bioelectronics. So you can actually make such piezoelectric material, and these are very important because these peptides are biocompatible, and you can actually, if you are thinking of synthesizing or designing some artificial organ, let's say you are making some heart, it will already do some mechanical actuation, and that will automatically generate the electricity. So this will be self powered, and you can see that these are showing this kind of butterfly loop which are characteristic for this piezoelectric response. So we are working in details, and we published this paper in Chemistry of Material this year. So now the last part, how much time do I have? Yeah, how much time do I have?
Yeah, you have
Yeah, you have time,
sufficient
sir.
time.
Sufficient time, sir.
How much?
15 minutes
5 minutes?
or even more than that. You please continue.
Okay. So now all these peptide materials, what we did is that we wanted to know what is the stiffness of such peptide materials, and for that we actually did detailed measurement of the persistent length and all this, and we see that the persistent length of such our peptide are actually almost equal to the actin filament. Actin filaments, remember, when in our body we have cells, right? And the cells are in some matrix. This is called extracellular matrix, and extracellular matrix has many of these microfibrils or neurofibrillite, actin, myosin, vimentin, collagen, many things are present. They actually give you that integrity of the cells so that they form tissue, right? So we see that our peptides have this kind of possibility. Then we thought, okay, excellent. Then what we will do is that from our such peptide material, can we now make hydrogels? If we cross-link this nice nanofiber, we can form hydrogels. And if we form hydrogels, can we use this hydrogel as a extracellular matrix for tissue engineering? I'm coming to that, what is there. Now, there was this very interesting paper in Science and also another one in Cell. They said that if you can tune the mechanical elasticity of such extracellular matrix, and if you take your stem cells, and the stem cells can be differentiated either in your osteoblast, that means very strong bone cells, or you can actually do it in cardiac muscle cells, or you can do it in normal neuronal cells. Okay, so we thought, okay, that is excellent. Can we really do that? So, and this is important. And if you don't know about hydrogel, what are they are like a material. This is actually a sol, but the hydrogels are the material when you self assemble like that fiber and which are cross linked, you see that it does not really flow. It is like that. And hydrogels are used for multiple things. Baby's diaper, that there also you have this hydrogel powder. So you put water, the hydrogel actually soak that water, and that's why it made all our parents life very easy, right? Baby does not leak. Okay, so this hydrogels has mostly water, and you can actually use this hydrogel for a lot of wound healing application and all. You can see over here, recently people are also going for 3D printing and these regenerative medicines where you can actually generate your own organ. So people are actually trying to, you can see that your ear, people are trying to create your ear using this kind of extracellular matrix, and then it will automatically form using the stem cells. So this is one of the thing, and you can see that hydrogels, you can see that if you have a burn injury there, this is an experiment done on the mouse. So you see that this mouse has got burn injury, and this is the typical dressing you do, and in this case you don't do anything, but here you put your hydrogel, and you see that the wound get actually healed much faster. Okay, this is the thing. And in the tissue engineering, what we do is that you take your cells, and you take it in the stem cells you can take, or you can take the differentiated stem cells as well, progenitor cells. So that cells, you take it in the material which you have made, and you put the material, And then what happens is that that material gives you the elasticity to form these new tissues. Okay. And so there are definitely a lot of things which are, and then tissues you can actually put it in your body. You can do that. You can do that in vitro culture and put it in the body, or you can also do it in vivo transplantation as well. But couple of things which are required is the mechanical property of these biomaterials. These are important. Then what you also want, that such biomaterials, after you form the tissue and the organ, these biomaterials should get degraded and should be actually gone. And then other thing is that this material should be also bioactive, because the bioactivity will make sure that your cells are actually going and attaching onto such materials. So these are important characteristic for that. And with that, I think I would like to just show you 2-3 slides more, that we took our peptides, and these peptides, they are all collagen mimetic peptides. And we thought that, okay, uh, can we really mineralize this peptide and mimic the bone tissue engineering. Now these peptides are collagen mimetic, and if you know this collagens, collagen structure and the tropocollagen, there is always a interstitial gap, and that's where this hydroxyapatite, they get actually precipitated, and they are like the glue. Okay, so we thought, okay, can we really do that? And we took our peptide, and this peptide we took, and then we put a bioactive glass material, which is what we do in mineralization. And then once you do and put it into with the bone cells, and we see that bone cells are proliferating very nicely, and they are taking the shape of the bone. And this is very important. And we thought, now we have done quite a lot of study, and this paper also we published last year. Our idea is that now can you now think of, like, many of you have probably a tooth implant, right? You have put some implant that is basically zirconia or something like that. It's an inorganic material. It is always going to be there. Now we are thinking that can we take our material, and this material we 3D print, just like you take the shape of your teeth, 3D print and make it something like that, and then put that thing in your can you really develop your original tooth from the stem cells, like, right? So you can actually have the bone formation, and you can actually transplant that onto your body. So nothing will be foreign, everything will be yours. And that is what is the fun of regenerative medicines. Now bone was rather simpler. We also showed for the cartilage, because many of the old people, they have this cartilage loss, right? The fluid that gets dried up. So then we are also trying to do some, the knee replacement surgery is rather a little bit cumbersome, and it's also painful. And so we thought of coming up with some injectable hydrogel. Along with another collaborator of mine, we are looking at also the cartilage tissue engineering in your knee. And apart from that, this is something which is very interesting thing, which actually we got result last year and we published this year, is that how to mimic the muscle, like cardiac heart muscles. As I was saying, most of our natural materials, they actually show such kind of strain stiffening behavior. You can see that if you apply force, it actually stiffens. Okay, but most of the other hydrogel material, if you apply force, just like toothpaste, you see, then they will flow. So we thought that can we now have a very interesting design when you have a very optimum peptide and polymer conjugate, and that's where we are working on. And it showed eventually very nice stiffening behavior, and we can actually mimic such kind of behavior. Not only that, we are actually now looking at generating this 3D print, and can we really make this artificial organ. So again, this is all basic chemistry which are done, but we do a lot of these different other physical characterization, so as to understand this in a much better fashion. So having done that, we are now looking at very interesting things. I will tell you this very interestingly. So many of us, we have this gastric ulcer formation. You know what is gastric ulcer? Now gastric ulcer means if you, in your stomach, you have pH which is much lower, right? But then what happens is that there are these bacteria that's called Helicobacter pylori that actually comes to your stomach, and it actually secretes some enzyme. There is something called urease. Urease, what it does is that it secretes urease, and urea, it acts on urea, okay, and it's developed ammonia. But if you develop ammonia in your stomach, that means it try to neutralize the pH from 2 to 3, try to make it something like 5, 6 or so that it can actually form very nice gastric ulcer, and it can actually live nicely. This is the way Helicobacter pylori, they actually form gastric ulcer. And when it becomes really more chronic, then you actually have this you have this the cancer, right? gastric ulcer, say cancer. This is how it happens. So we thought that can we really mimic this kind of behavior using this, just like the strain stiffening I showed, that we can actually take this urease and elastase enzyme, and we take this kind of peptide material, conjugate it, and then can we really see that kind of stiffening. Now when you form this gastric ulcer, then what happens is that the stomach epithelial cell that becomes stiffened. So what we are currently doing now at the moment, then this paper is all will be submitted next month, is that we can mimic this entire system. And this is very important because you can then fool your body from this kind of system, and you can alert your system. So this is many of the things which are going on in the lab. And I hope to summarize, we showed some of the example that where we have this very nice healing behavior, just like a natural system. We also showed very nice functional control to show catalysis, piezoelectric behavior. We can show there's very nice orthogonal control. We can have two different creations. And at the end, I showed that, you can have biomineralization of your peptides. And then what you can do is that you can have very nice bone tissue engineering, or we are actually going throughout making strain stiffening material that eventually we want to take it for cardiac muscle stiffening example. And also this is entire thing we are working. And this process wouldn't have been complete without the active collaboration of my many of the collaborators. Many new collaborations have also been added, and many of the group members, many of them are now gone for postdoc abroad, and this is the current group which we have at this moment. And generous support from the funding agencies, and also for your kind patience. Thank you.
Thank you, Dr. Paul, for the excellent and enjoyable talk on the journey of nanotechnology and the vast application of the nanotechnology. Now, I request to all the participants to ask if there is any question, then you may ask to our sir.
Yeah, I'll be happy to answer if you have any query, any kind of query. I mean, I think I rather showed because I was not sure what is the. I gave a glimpse of more or less everything so that you have an idea of what things are going on.
Sir, may I ask you one?
Exactly. This was just a proof of the concept, just to show it can be anything. Okay, it can be any of the drug which can be loaded onto it. It is much more general.
Okay,
It's
only
just
to
showed. That was the only that example, proof of principle. We have shown with other drugs also. We are now doing with budesonide and many other drugs.
Okay, okay. Actually, the temperature is temperature comes due to different reason in for different diseases. So that's why I'm telling, because doctors usually prescribe different types of paracetamol for different diseases. That is why I'm asking this.
Yes, yes, that is absolutely, that is right. Different paracetamol. Our idea was that can we really, the doses doctor decides based on the excretion from your body. And you are taking a lot of medicines. We thought, okay, can we really load it into a nanoparticle which will circulate in your bloodstream, and as soon as it finds that there is a temperature rise, can you really start releasing it in a burst release fashion? So you don't need to take multiple times. You might not be taking medicines and all this. So yeah, it will be there in your body and it will automatically do the job.
Yes. So another question is, you use in for 1D, 2D nanostructure or whatever you have made. So whenever you are working with coumarin, as we know, coumarin has
cyanine molecule, then we put some other kind of molecule. That was a different one. I showed actually multiple things. Sorry for that. But then, yeah, it's difficult to pack things all together. These all different things can be a different topic for,
And the
different.
in vivo tissue engineering, it needs a carrier. So what carrier did you use for this tissue engineering whenever it is doing in vivo pattern?
So what I showed here at the moment, that bioglass work, that's where we have not yet gone to in vivo. Even that cardiac heart muscles, there also we have not done anything in vivo. We are going to start from next January. Okay, these are all very interesting material. What we did with that, I did not show here. That was actually with cartilage tissue engineering. And the cartilage tissue engineering, that majorly it was done by my collaborator. That was not my this thing. So Dr. Deepak Ghosh. So that's where we took a different kind of extracellular matrix where we have a polymer and we are actually incorporated a little bit of peptide. So this was like an interpenetrating network. Okay, and that's where we hosted our project chondrocytes. Okay, and then it actually forms very nice differentiation of these chondrocytes into these cartilage tissues, which actually now still it is going on, and I think they are talking to the patient from PGI Chandigarh, so they are looking at this knee transplant. Yeah.
Okay. Thank you, sir. The talk is very fascinating and very interesting. We enjoyed.
Thank you.
Sir, one small query, sir.
Yeah, please go ahead.
Sir, is there any possibility when a drug is prescribed as a medicine, and when we are taking this medicine, generally doctor prescribed according to our lethal dose, is there any possibility or any failure of drug mechanism that the small quantity of drug may be incorporated in our body as a toxic dose?
No, that's a very valid question what you are asking. The doctor always decides on the dose, that because see, there is something a therapeutic window. If you give too much of drug, then that is actually creates side effect in the body, that becomes toxic, right? Too much concentration, and then you also take this intermittent gap you take, right? That's how doctor decides the dose. But now the thing is that you would all agree that that a lot of drugs we take in our body and they are of no use, they get actually secreted. It's just that we have to maintain the therapeutic window. That's why you have to take such a high concentration. So the idea is that now the way we are going towards is that can you now have nanoparticle, which are intelligent nanoparticle, where we put our drug and it will actually go, it will circulate in our body, and it will be really nice. It will go exactly the place where it requires. Okay, maybe you have inflammation somewhere, it has to find that inflammation site and it will go there. Then what will happen, even if you have taken very less amount of drug, all the drug will actually go there and it will actually increase the local concentration very high. So you don't need to really maintain the concentration in the entire body, so your side effect will be much lower. That's what I meant by saying a letter with address to, let's say, Dr. Sajal Das. So this is what it means. It needs to find that recognition in unit, and so people are looking at this kind of biomarker so that it actually intelligently can go and deliver it. So your side effect will actually, because many of the problem with the cancer and nanomedicine is that you have a lot of side effect, because it not only goes to the cancer cells, it also kills the normal cells, right? So how can you really dictate that? These are the recognition thing which are very interesting and which are going on. So yeah, it's not so easy, but then yeah.
Exactly, sir. Thank you.
Good evening, sir. Hello, sir. Hello. Sir,
Yeah,
can you hear me?
Yes, you are audible.
Sir, can you hear me?
Please ask your question.
Yes, you are audible, Sanjay.
Sir, it's a fantastic session. So I have a query, sir. When actually you mentioned that drug molecule through nanoparticle, it can be injected or it can be taken through oral. So question is that when it is going to the particular cell or target cell and painting the cell and going to the target point, if there is any chemistry working or it's a only biological interaction.
No. Biological interaction is all about chemistry only. So basically, see, when you are putting the drug coated in a nanoparticle, particularly if you are going for oral route, see, injection mode is rather easy because you directly put it in the bloodstream and it goes into the bloodstream and it actually gets circulated. Okay, so that is okay. That is not that much challenging, but the challenge comes when you actually go for a oral route delivery. And because the reason is that if you now take a nanoparticle and put your drug molecule into it, as soon as it actually goes through your oral route, that route will have multiple pH shock. It will, right? And if your nanoparticle, which you have made it, of course, it has to be resistant to such extreme pH, which actually it goes through. Because after that only it will come to the bloodstream, right? So chemistry plays a very important role, and you have to protect that nanoparticle against such kind of pH, extreme pH changes.
Okay, thank you, sir. Thank you, sir.
Yeah, does it answer your question? Am I audible?
Is there any questions?
Yes, sir.
Yes, sir, you are
Yes,
audible.
Dr. Sanjay, sir, you have any questions? You raise your hands. If you have any questions, please ask.
I already asked. Another query is that, sir. Another query is that my former colleague, Dr. Sujit Ghosh, already mentioned regarding the toxicity, and it is I read in a article that if the residue will not be extracted by urinary tract or it may be deposited in liver or spleen.
That's right,
So,
absolutely. That is where the toxicology comes into picture, and one has to really validate such nanomaterials against such kind of things. Is there any selective deposition or in certain organ or not? So you need to do a lot of this, and also histopathology. Many things are needed. You cannot just use it just like that. So obviously, it's a valid point.
exactly. Thank you, sir. Thank you.
Is there any questions? So may I close all this? You have any
If there is
query?
no question, actually, maybe let me tell you a
I
bit.
think there is no more questions. I think there is no more questions. So good evening, everyone. On behalf of UGC HRDC, University of North Bengal, I am glad to express a vote of thanks. Special thanks to our resource person, Dr. Ashish Pal, Professor at Institute of Nanoscience and Technology, Mohali, for accepting our invitation and being with us today. Your thoughts and suggestions truly inspired us and have enlightened our minds. I thank to our coordinators at UGC, HRDC, University of North Bengal, Hello, coordinator
You are
sir.
not audible.
Yeah, actually, Professor Pal has already left, so maybe let's end this session here, and we'll be meeting tomorrow morning. Thank you all for your kind patience throughout the lecture.
Thank you.
Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.